So, hello everyone for another year of exciting Force Talks. It's 2023 and the Force 2020 group has its Zoom meeting, and we will see and have great talks today. Let's have a look at the agenda. I try to share my screen and then we can have a look of the talks that we intend to have. So, right, so we had some early Force Cafe just in the hour before we start this session, and had very interesting discussions. So whenever you want, please join us also up front. Yeah, now we're in the official formal presentation part. And our first speaker is Alexandre Dumont, and he will talk about emulating CPUs, especially a 6502 microprocessor, which was the core of lots of home computers. And yeah, I'm very happy to have you here, and let's see what you can tell us. So the stage is yours. Please go ahead.
Hi, can you hear me?
Yes.
Okay, all right. I'm going to share my screen. Okay, can you see my screen?
Yep.
All right. Okay, so thank you, Rich. Thank you, Peter, for organizing the meeting, and thank you for watching, everyone. Today I'm going to present you this latest project I've been working on in Forth. It's about creating a 6502 emulator in Forth. Okay, so it's not changing. Yes. Okay, so well, I guess you probably know the 6502 was a 8-bit microprocessor. I think it was born in the 1975, and it was very popular, and it's still a relevant microprocessor. It's still used today, and still there is active R&D development. The development of this project I started in late December, so last month. First, I started to develop this emulator in AlexForth, which is my fourth implemented on 6502. But then I moved to GForth, and the idea is to later try to adapt it to ESP32Forth. The first objective of this project was to be able to run 65CO2 ROMs. So I load the file in a binary form and be able to run it. And as a spoiler, at this stage of the project, I'm already able to run my AlexForth in binary form, loaded into it. So well, it seems to work. So the overall approach about approaching this project, I use the WDC 65CO2 datasheet as the main reference. It's where all the instructions are documented and all the registers and everything. And as you will see in the presentation, I've tried to replicate the main components of the 6502 in Forth. So either with data structure or with words to manipulate them. When I started the project, I had clear that I wanted to start with very simple instructions. So like load A or store A. Load A is load a value into the A register, while store A is store the value from the A register to memory. And as you will see, I've tried to take a very systematic and mechanical approach. I think for me it was critical for all the definition of the instruction, and then it helps me a lot grouping and then factoring the words. And I think the result is I think the code is quite clean. And about factoring, I try not to factor too early so that I can see clear patterns to emerge, because I think that helped me a lot as well. So about the data structure that I have implemented. I've started with the register. So the 6502 has several registers, a very few of them. Most of them are 8-bit, except the program counter, which is 2 bytes. So what I've done is simply create the variables to hold the value of the registers. Through the word presentation, whenever we see a black box, it's a piece of actual code from my MU6502 emulator. Then there is also the 6502 processor flags. For that, I have created values with the masks for each of the bit, because the processor flags, it's an 8-bit, it's like an 8-bit register, and there are, I think it's 7 flags. So I've got these masks, and then I've defined some words to clear and set and update the flags. And with these words, I've been able to, I have created some a little bit higher level words that set the N flag, set the 0 flag, overflow flag, the carry, and get the carry and the decimal flag. Regarding the memory of a 6502 is at most 65K bytes. So what I've done is simply allocate a 65K byte array in memory. It's called RAM, and that's it. And then I've implemented a couple of words to fetch from the target memory, fetch a byte, or store a byte in the target memory. And then I've got also a word to fetch 2 bytes at in the same operation. Regarding the program counter, we've already seen it's a variable, and then I've got a couple of words to fetch a byte at the program counter and advance the program counter by 1, or fetch a word, so 2 bytes, at the program counter and advance the program counter by 2. Then we're getting to the meat of the 6502 emulator. The 6502, the 65C02, sorry, has 212 valid opcodes. All of them are 1 byte. And so what I've done is allocate an array of 256 cells to be able to store the execution token of up to 256 fourth words. So that's done like this. And so the main idea, as you will see in the next slide, is I've defined words for each of the opcodes. And what I do is store the execution token of each of those words in the opcodes array. And when we will decode each of the opcode in the memory, we will just index into the opcodes array to obtain the execution token of the word and execute it. So thinking about this, I've defined a word, it's called next, to run the next processor cycle. And what it does is simply fetch a byte, which is the opcode, at the program counter position in memory. We decode it simply by obtaining the execution token from the opcodes table, and then we execute the word. And then, so right now it's almost done. We just have to repeat this in a loop. So let's have a look at how I've approached the instruction definitions. So I've defined a word called bind, which takes an execution token and an opcode, and it simply stores the execution token in the opcodes table at the opcode position. So the idea is I can define anonymous or no-name words and bind them to an opcode, and that's it. So as the simplest example there is the no operation opcode is EA. So I define a word which does nothing, like this. and I can bind it to the opcode EA. So whenever at the program counter we will find EA as the opcode, what's going to happen? We will fetch from the opcodes table the XT, which is the XT for this word, and we will run it, which in this case will do nothing. So let's have a look at defining more complex words, but still simple, like LDA or STA. So the LDA immediate, we take a value. So the instruction is 2 bytes, it's A9 for the opcode, and the operand, which is 1 byte. Here is XX. So here is the definition of the word. We just take 1 byte at the PC, which is the operand. We set the flags and we store it in a register A. So we define that word, we bind it to A9, and that's it for this word. Very similar approach to store A absolute. Opcode is 8D, and that would be the definition of the word. We just get the value in register A. We retrieve the address, which is right after the opcode, and we store it in memory. So basically that's it. So well, after some instructions are more complex than this one, but still, let's have a look at the addressing modes. So the 65CO2 has 16 addressing modes, although not all of the instructions all use the 16. I think LDA use 8 or 9 addressing modes. So the first line is the word that we've already seen, so it's low day immediate. And then I've put here the definition of 8 or 7, 8 other low day version with different addressing modes. And it's the non-factored version that we see here. And when we look at that, we can see that this part is repeating in all the words. And there is a clear pattern here of, well, the pattern would appear more clearly maybe if we would look at the same definition for store A and LDX and LDY. So, and what happens is that all these same word will repeat for all the instructions. So patterns start to emerge that show opportunity for factoring here. Let's have a look at how it how I have factored the words. So what I've done is I've defined this word, tick ABSX for absolute index with X, tick ABSY. And so we've got here the definition for new words that replace these sentences here. And now I can use them in the previous definition that we had of the LDA words. So we've got, we've replaced from the previous slide, these pieces here with this addressing modes words. And also, I've replaced here with only one word, which I've factored at the top. So the flag and store in the register A, now it's an LDA word that I reuse here. And if we look at the definition for all the store A instruction, we can see that it's basically the same. There is a very few, I think it's very, very clean, because if we look at the amount of force code, there's very little. Really, the only force code there is this here and this. That's it. There's very little to do. Also, I didn't want to write all these templates by hand. If you see, all my words are formatted the same. So for all the 212 instruction, I've generated an empty template code using a spreadsheet. I had, from a previous project, I had a spreadsheet with all the 212 instruction with all their opcodes and addressing mode. So I I've made a formula in the spreadsheet to generate an empty template and pasted the result in my file, in my code. And then I just had to fill all of them with the definition. And that helps me a lot because I didn't have to write all the opcodes by hand, and it removed a lot of possibility for errors. So now let's have a look at some more advanced stuff. For example, handling input and output. In the 6502, the input-output is memory mapped. So in this case, I think it's quite easy to enhance the emulator and support any I/O that we want. For example, if we are in a terminal, like in the demo I will show you in GeForce, it's quite easy to handle input of or output of a single character, because in the previous definition of the fetch and store words byte in the memory, what I've added is just this part. So if I've defined a couple of addresses in memory, so it's F004, F001, which stand for a character input or character output. And in that case, if we want to fetch a byte from this F004 address, instead of fetching it from RAM, we just get the character from the input. So it would be the keyword. Or if we store in the F001 address, it's going to emit the value instead of storing it into the RAM. And with this mechanism, we can extend to whatever thing we want. We just have to define more addresses and hook into these words and replace the behavior. So it would be easy, for example, to write to a specific register of a microcontroller. If we are on ESP32 for example, we could perfectly interact with the GPIO pins from this 6502 emulator. So what I've defined, I already showed the next word, which just run one cycle. I've defined a run word, which start to a loop and just run the word next in a loop. And also there is a small breakpoint facility. So breakpoint is a deferred word, and you can implement whatever breakpoint you want. So whenever breakpoint is returning true, the run loop will end. So for example, here we have an example of a definition of breakpoint. If the value of A gets the value 1, it's going to return true, so it's going to end the loop. Well, I think that's a good time to do a small demo. So, okay. Can you see here the terminal? Yep.
Yes, we can see it.
Okay, great.
Yes.
So I'm going to enter GeForce and load the code. And from here, let's have a look at the first very simple demo. So in this demo, what we are going to run, so it has already loaded into the target memory these 4 bytes of code. And there is the opcode A9, which stands for load A, and it's going to load into the register A the value 12 in hexadecimal. Here, my GeForce is set to hexadecimal, so whenever I type a number, it's always hexadecimal. And then it's the second instruction is store A, and it's going to store the value of A into the address 0030. So let's have a look first with status. We can see the register, so we can see that the PC is at 600, so that's here. And the value of A is 0. Let's have a look also at the position 0030. 30, and we will get the byte. Okay, we print it. and it's 0. So we have 0 right now at this position in memory, in the target memory. Target memory is the memory of the 6502, obviously. So I'm going to run the first instruction. And here already we can see that now A is 12. Okay, I'm going to run the second instruction. And we don't see anything here on the status on the register, but let's have a look at the content of this position. And yes, now it's 12. So this is working right now. Okay, let's have a look at the second demo. If the demo is a little bit more complex, but I'm going to explain, so it's not complex, not that complex. The first instruction is 2 byte. It's loading the value 61 into the register X. And then it's storing the value of X into the position in memory F001. If you remember, F001 is a special position in memory. It's not going to store in RAM. It's going to show it on the screen. So it's going to print the character, to emit the character. Then I increment X. I compare X with 7B. And if it's not equal, I jump back to this position. Sorry, this one. So we have incremented X, and we will store it again on printing it on the screen. So if you've noticed, 61 is A in the alphabet, and this is the last letter will be right after Z. So if we run this, we can see that it has printed all these characters on the screen. And then there's a break, and right now there's a breakpoint on the break instruction. So well, I hope it demonstrates that it's working. I've got the demo 3. Yeah, okay. Demo 3 is about running my Alexandre monitor. So it's a 6502 monitor. Okay, I can do it. Okay, Alexandre. And it tells us, okay, execute Alexandre, go to this position, and we have to type this into the memory and run it. We can do that as well. So I'm going to 3000. Here I'm going to store A9 F. Okay, no, FF 85. So here we are already running 6502 code because we are in the monitor. This is my own 6502 monitor, and it shows where we are in the memory, and each time I type a byte, it's storing the byte into this position and incrementing the position. Okay, if we go back to 300, we can see that now at that position we have the value that we have entered previously. Yeah, here. A9FF 8530. So I'm going back to 300 and I'm going to run that. And we can see, okay, it has exited because there was a break. So because there is a breakpoint in the emulator on the break instruction, now we are back into GeForce. We have exited the emulation of Alex monitor. And we can see that it has run. So the load A FF, we can see that A is FF. And I think it was storing it in the same memory position. So it was 0030. And let's see. Okay. And we can see, yes, it has stored. So this 8530, it stores A FF into the memory position 30. So that worked. Okay, and the last demo really that I have is just demo 4. So I'm going to load, if we see the definition of the word Alexandre, it simply loads this file, fourthemu.bin, which is the binary for my fourth Alexandre for the emulator version, because it's not the same addressing and such. It loads it at position 8000 in memory, and then we reset the program counter and run it. So let's do that. Alex Force. Okay, I'm already in it, but okay, wait, that's it. We are now in Alex Force. So this is not G-Force anymore. If I type this, you can see it's not working because Alex Force is case sensitive. So I can put things on the stack, sum them, and like if I do .s, okay, it shows the. You can see the interface is slightly different from G-Force. It's similar, but it's not. This is G-Force with some spaces, and this is Alex Force here running. So the Alex Force is running right now Force, but in a 6502 version in my 6502 emulator running in G-Force. And well, I can and that works. Yeah. So that's basically it. I don't know if you have any question. Maybe I don't know if Christian is here. Christian, do you have any question?
Thank you very much, Alexandre. That's really great.
Thank you. And if you want to have a look at the code, so the code, okay, yes, I've got a couple more slides, but just thank you.
Proceed.
Yeah. So yeah, sorry. The limitation right now, I still not have implemented any support for interrupts. So all the words for interrupts and this kind of thing, it's non-existent right now. And the emulator is not clock cycle accurate. And I don't think I will develop that in that part. And possible idea for future updates. So I would like to try to port. I think there will be some modification of the code, but not much. Port everything to ESP32 Force and do some basic I/O capability for handling the GPIO ports and the pins. And probably I will try to add also some interrupt mechanism. And I don't know, maybe you develop a GUI or something. And well, thank you for listening to me. And if you want, in the slides, you will have links to the code, my webpage with all my project, and you can find me on Twitter. And also remember, yeah, there is the meeting archive here at this link. And if you, yeah, the code, I was explaining earlier that the code is very, I don't know how to say, very structured, very regular. So you can see that all the words, they have the same appearance. So it's all no-name words.
Alex, I have a question.
Yeah, sure.
Does this have any inspiration on Jan Langevad's emulator or simulator?
No, I've not. I've opened his code, yes, but I've not looked at how he did his emulator because I started right away in my direction as I explained. So I don't know if there is any similarity or not. I've not looked at that.
Yeah. So Alexandre, did you do any benchmarks? Sorry, Klaus.
No.
Yeah, I wanted to ask the same question.
No, I did not. No, I did not. No, really, I don't know how this would perform. At no point I was not interested in making the code fast, or I first wanted it to work. So right now I'm quite surprised actually that it would work so well. Well enough to be able to run my Alex Force, which well, it has a lot of addressing modes and a lot of instructions. The most complex instruction I had to make work were this add with carry and subtract with carry, especially because in the 6502 there are two modes. There's the binary mode or hexadecimal mode,
BCD,
and the BCD mode. So the BCD mode was a nightmare, and there are some leftover. Yeah, really, it was a nightmare because you have to handle not only give the right result, but also all the flags.
Alex,
So,
I have another question,
Sure.
and this question is for Klaus Schleisig to know and make him aware, also to Ulrich. For how long, when did you hear about Force, and when did you began? When was your beginning with Force?
I think it was in 2021, I think.
Yeah.
Yeah, in April 2021. Yeah.
This is what I mean. This is what I mean.
I started with writing my own fourth. So really, this project is, I would say, my first fourth project, because the previous one was more of a 6502 assembly project, writing a fourth. And
there are a lot of people in the maker communities and in the microprocessors communities and in hobby that never heard about force and are intelligent and are young, like Alexandre, and they are excellent programmers, and they need to know about force, because it's a pity if those guys don't know how to program with force. It opens another world.
Yeah, Alexandre, I want to congratulate you that after such a short time, you are writing excellent force code. You obviously have understood what it is all about.
Yeah, I think so. Yeah.
Thank you very much for your congratulations. But I was really surprised, I have to say, because when you look at it, almost everything is comment. So all these columns here are common. This no name is, well, it's not relevant. So really, what is the code is just
the essence.
This here, this comment, this in the middle, and this, and that's all. That's all there is.
The code is the essence. Yes, that's great, and that's what
I think it's probably a virtue of forth, because it stays elegant and it's very compact. It's super compact.
When in that case, we need to compliment you 2 times, once for the code and once for the comments.
Okay. Yeah, because it's most of it is comments, really.
All right.
I still have one question for you.
Sure.
Did you also implement the indirect jump error?
But no. I didn't look at it, so I don't know how it's going to behave. Yeah,
do you know what it is?
No, I wouldn't know. I don't think I know.
Oh, it's
about when it's crossing pages.
It's when it's crossing pages. Yes,
I read about that, and I would need to try. I don't know. There's probably a benchmark or something to.
Yes.
Yeah, and there are also some invalid opcodes which I have not defined.
Yes,
so,
but a lot of force systems did crash after minor modifications in the early days because this error.
Mm-hmm.
Yeah, I don't know how it's going to handle it, so it might crash, and that's something I have not really. I try to test. Where is it in the code? There are a lot of command. I tried to implement some words to do test, but really I didn't write any test. So, because I think I should put some testing in there to ensure that it works.
Okay.
But right now, I just did some testing running code, and that's it.
Yeah, it's not very important, but I was wondering.
Well, right now it's not an industrial solution, so just for me, it seems to work.
So we admire it very much. Are there any other questions?
Well, I don't have a question, but only a comment, and I can really learn a lot of this coding. So I'm looking forward to getting a copy of the code so I can tune my own system. I think I can reduce the size by 90% or something like that.
And here you have the links.
Yeah. Right. Thank you very much. I hear an alarm clock ringing. Great. So
how do I unshare my screen?
Yeah. Well, I can assist in that. No, it should be gone.
Okay, stop sharing. Yes, sorry.
Yes.
Thank you very much.
Here we are. You're welcome. So thanks for this great talk, and I'm looking forward to seeing more 6502 programs running in the future. Our next speaker will be Pablo Reda, and he will talk about some formatted printing, I guess, which he implemented in his 4th R3 dialect. And so, Pablo, please go ahead, share your screen. Yeah, here we are.
see
I
my
can see
desktop?
it. Mm-hmm.
Yep.
Okay. Here. Well, it's a teeny chat about how implement PRINTF in 4R3. PRINTF is a common instruction in C. With PRINTF, I can show in the console with a format defined with a string. For example, when say in C this command, the console replace the percentage D with the number give for the function, and try to emulate or implement this instruction in my form. The idea is traverse the string, and when found a percent character, this position with the value get from the stack. The idea is make a word who make this. Some difference from my form for better clarification is in my form data and code has in separate memory. The dictionary in runtime not exist, but I have a free memory and use like a dynamic memory. I can define a buffer with name, and when I refer to a address, I use the prefix quote, single quote. For example, this is a word defined in the libraries, comma C, put a byte in memory and an increment in the frame memory. First, for implement this functionality, I need words for convert the value to a string. And this word, for example, for a decimal, for print a decimal number, this is the word for convert this value in the stack in a buffer of memory when I store the string of the decimal number. Well, first remove the sign, the thing, and test is the unique value of if you take the absolute. This is a 64. This is a 64 bit length, and this is number is the unique name when you take the absolute value, you have a negative. And then prepare the buffer, divide by 10 and store every character in this buffer, and then add a thing if need, and return the string in the address of the string in the stack. Well, this is the ASCII table, and when I don't like to compare everything in the string for trigger the the word for convert every number, I only take the lower 4 byte. And for example, when I found %d, then jump to the 4th position. This is the idea. The basic loop is this is the word for print in memory. I have in the top of stack the string and consume values from the stack when found a percentage character. The traverse the string is made here. This parenthesis and the conditional in define a while loop. In this while loop, get a character while not 0. 0 is a final of a string. Emit this character and emit this character if the character is not percentage character stored in memory and terminate, and if is percentage remove from stack, get the next character, make a mask for the lower 4 bits, multiply by 8, add to the address of control, control is a list of address of code. For example, in D, I mark my, for example, in %d, the word who is called is C4. And the word C4 is take the value of the stack, generate a buffer with the string representation, and copy to memory, and end. This is the basic word of printf. I show you in example. For example, this is the initial test. I run and I get the 2 values passed by stack, and make a loop showing the counter. If, for example, I use binary, now I have the loop in binary format. The implementation of real printf is here. This is the same code. He is all the words for every character in nibble in 4 bit, fixed point, hexadecimal character, and some are usual. and the words for hexadecimal octal fixed point with 4 decimal numbers, with 2 or with 1, and this is all. This show how implement printf in 4R. R3 and to memory, count the characters, and make the system call to print in console. And that's all. Thank you to all for group, and question are welcome.
Thank you very much, Pablo. That's really great. And
very good, Pablo.
And it's so simple to do it. I think you showed us the example in R3, but it was so understandable. I think everyone can pick it up and see how it works. And we will probably see similar implementations of your idea in other systems. So are there any questions?
Well, I have a question.
Yeah, sure.
Is implemented the right alignment, the minus sign, the hyphen to right align the string? The question arises from the last example you show, the binary, that I would like to see the binary right aligned. Okay. A suggestion. Okay. More than a question.
You say binary.
If you put a percentage minus, and I don't remember very well the syntax of PRINTF, but I remember that there is a way to right align the number, putting an minus, an hyphen in the front of the letter. I don't remember well.
Yeah, if you have a negative length of the field, then it's that's the way to make it right aligned. Yes.
I not implement every flag and combination. Only the basic. But yes, this complicate the implementation. I try to make all more simple possible.
The next challenge is this. Okay.
Okay.
Are there any other questions? Well, then thank you very much again. I find this very inspiring, and yeah, I didn't think about having PRINTF. Yeah, but it seems to be very easy. Our next speaker is Willem Ouwerkerk, and we will hear something about robots.
Yes.
Willem, please.
I will. Okay. Did I succeed sharing?
Yes. We see a Windows desktop to the left and some, and now we see a Windows desktop to the right and some robot.
Then so it's full screen.
Yeah.
Yes. For a while, I wanted to show you some of the robots I did build over the years. And starting with the first autonomous one, and that's this one. It's called the Opodeldoe. And one of the nice things that it has also 6502 derivative on board. In that time, the only microcontroller I could get of was the R6501Q. And there was also a fourth version of that, and that was the R6511Q. That had a fourth core in ROM on board. But this one I designed myself. I did build the board and write a board for it. I can't remember which version it was, if it was Pickford or 79, something about that in that age. And then we come with, and I did build a lot of robots for exhibitions. This one is a monkey-like robot. It's named the Slingeraar. And it lives on a steel wire with a nest on one side and the feeding on the other side. So the wire is the world that we live in. Its nest is our safe home. And we need to eat, so to live. So, and same with this robot. He likes it very much to stay in his safe place, but he needs to come out sometimes. And I did use sensors so that the public could please him. Now, this one, with this robot I made on an exhibition, a field like a robot zoo. Dus on top was the monkey, and lower there were some other robots. This is the monkey from the backside. Below you see the 8000 C535, it's 8052 derivative. Board with also with our own Ford on it. It was 8051 Ansford. Dus that one had an early version of Ansford on it. This is the front with sensors and feeding wires. And also on the low part of the screen, a little study about the movement. These kind of things I do a lot for walking robots. But this was the first robot I did the width for. The next one is a cord dancing robot. That's just a simple robot arm, but it emulates bird dances when they are courting. And it also reacts on a lot of sensors, and it has 5 servo motors to control it. Later on, I'll show you a small demo of it. Here it rises up. This is a ball robot. It was a robot herd. It was part of the robot zoo with the robot monkey, and it were 7 small robots communicating through infrared, and the communication was used to control if a partner was nearby. And that's why it's called a herd. They try to keep together. They only stay together. And that was the game with it. I had 9 lights in a large square around them, and the lights lured them. So they constantly were changing direction. And sometimes they lost each other then. And then they were in a large panic, beeping and running around trying to find the others. In this case, I used Byteford and an 8089 C2051 controller, also an 8051 derivative. Very small microcontroller with only 2K of flash and 128 bytes of RAM. It's only very little compared to the modern microcontrollers. Here this is the inside of the balls, and below the balls in action. Here's my big mean sniffer. With this robot I did manage to get on the local, a national TV in a program about strange things. And this one was, this robot was meant to bully people. So it was placed in a large room, and every time somebody entered that room, the robot follows them, and a little bit too close. And it was you can say it was an implementation of myself. I like to touch people, and this robot does the same. It comes a little bit too close for comfort. And it's also running on the 8051 Ansford and 8052 derivative, but it has also smart sensor units with infrared and ultrasonic. It was not easily available to, so I built it myself for this robot. And the computers were in a small network. So it was a main computer and a sensor network. All running Ford, of course. This robot I built as a commercial project. It was meant to demonstrate the ASI interface. It's still available. So it has on board some ASI interface units that talk to and also a 8052 derivative board. It was quite a complex project. There was a lot wrong with the controlling hardware. A lot of times the chips driving the motors were going up in flames. Now we come to our current project. This one I built for the Eagle project. It's a simple biped with 4 motors, ultrasonic distance meter, a LiPo accu, and some additional circuitry. That's for power supply and to control the voltage of the LiPo, so it doesn't blow up. This is version 1, a more attractive version with the same hardware, but a little smaller and a little funkier. This is the inside. You see at the right the distance meter. In the middle you see the brains, and below you see a LiPo accu and some control circuitry. And the controller is right on the bottom, and it's a small MSP430 GT2553 running NoFord that I built with Albert. Oh. And on the lower side you see printed parts for the robot, a leg and a feet. Then we come with quite a bit more complex one. This one has 18 motors, and it walks like an insect. And what can I say about it? You see, there's quite a lot of wiring at the lower photograph, and also movement patterns were used a lot here. So I have a small apron with a lot of different movement patterns in it. And I need to say that I did have a lot of use for Albert's so-called pili-plop algorithm. And the pili-plop is a Brazenham-like algorithm that controls as many processes as you like. So in this case, it's 18 or 20 motors. And they all go simultaneously from one position to another. So it gives a very nice fluid movement. And the only thing you have to do is put the pili-plop algorithm in between your software and the motors. Here's some different version. This is version 2 I'm currently building. And at the lower side, you see the hardware, the electronic hardware, with left were the ultrasonic sensors, the servo motor, In the middle, you see the processor unit with a Bluetooth module on it. And on the left, power supplies and LiPo security hardware. This is what I'm reasonably proud of. This is a leg with touch in it. It's very simple touch. It's just a spike. When the leg touches the floor or any other subject, it is pressed and you can signal if the leg is standing on a hard subject. So it gives the robot a touch. Very primitive, but it's really nice to have. It makes walking even nicer. Here's the robot. The robot is booted and communicating with the terminal left on the screen. And on the right side, there's an editor open that loads software parts in the robot to test. This communicating is through Bluetooth. This is schematics. In the middle, the CPU. It's the MSP 430 F149. On the left upper, there's an EEPROM with the movement patterns and a lot of capacitors and a lot of connectors. Here we come to the USHI robot. The USHI robot I did design for our club. We wanted to have a robot teaching platform. And we designed also some games for it. It has a hardware with for different microcontrollers. The setup boards can contain 8051 derivatives or AVR. And this one is an early AVR, the 8090S2313, I think it was. Nowadays, it's the same processor is still available, but it's called the 80Tiny. So it has a little, it has some hardware changes. At the back, you see some motors with wheels and an infrared communication unit. It's a transmitter and a receiver in one unit. At the front, you see a simple infrared distance meter and some additional hardware. The lower photograph, you see the parts added for drawing on the floor, and it's a sensor that detects the movement of the wheels, and the processor counts them, and it has a nice correction mechanism to draw nice straight and curved lines. That you see an experiment with that here. I put a small piece of paper on the floor and did draw a dotted line. And it was the first test. It was nice and straight for just a simple robot. Here he is with at the back side the pen and the pen lift, and you see the wheels with the motion detectors. And at the front, we have an ultrasonic distance meter. At the time I did design it, they were not easily available, so I did design one myself, and I called that MUS, for mini ultrasonic distance meter. Then we come to my latest project for the club, that's the COSY. This is version 1. It's a small PCB with a lot of hardware on it, also a Bluetooth module and infrared distance meter, and also motors and servos are fitting on it. Here you see the next version of that robot with a little nicer motor with a nice gear set, and also a little 3D printed piece to fit the motor on the board. and so you can connect it only with one tie wrap and it fits very firmly. At the lower part you see the 3D printed wheels with motors, of course, and here we have it completely built with whiskers on the front and back side. It's a small servo to control the ultrasonic distance meter, so it can look around. A small OLED for testing. You can test sensors easily and adjust them if necessary. Here we see it on my game board. I made this game board also for the club. We did a workshop one afternoon where everybody wrote a line following program. And here we have also the schematics. At the right side you see 3 drawings of CPUs. On the cozy it is possible to fit 3 CPUs on it, an AVR, and 2 different MSP processors. On the top you see here the motor driving unit. Here we have the power supply, and here we have the floor sensor unit. And the floor sensors are infrared and are switchable by a small I2C LED driver. Now, there are more details in it, but maybe I can talk about that another time. It's just an overview. Here we have the 3D printed bumpers, and we have some additional 3D parts, a cover for the gear, the wheels, the LiPo accu with a little bracket, also to make it more easy to build. Here we have the front, and we see there are 5 infrared sensors to detect lines and table edges and so on. And below the picture we have a Bluetooth transceiver, an OLED screen, in the middle the CPU, and at the right you see again the ultrasonic distance meter, and below it a servo. Now here we have our first winners of the first workshop. Some of you know Jeroen. He's a very nice person and a good programmer. And on the right we have Henny, and I'm in Henny with a project building a wireless controller network. It's also partly on Project Portworx. Here's my latest project. That is a bird robot. I'm building it with a local artist. This is the sketch of the inner workings of it. How do you call it? This is the spine.
Skeleton.
The skeleton. That's the word. Yes, thank you. And you see also the basics of the wing. Not yet feathers on it mounted, but that's the next step. Here we have a picture of the metal prototype, with some 3D printing on the neck and head, and there's some metal work for the snavel. I can't remember the English name of it.
The beak.
Yep. And on the below side we have the movable neck. You also see it on the upper photo. With that you can move the neck forward and backward and left and right with 2 servo motors to give it more functionality. Here we have the tail. It's a tail with feathers, and one of the purposes of this robot is we call it a charming robot, and it's going to charm the visitors. They are walking through the park where it's meant to be. So it's showing itself by jumping high in the air, and then it falls down, and while it's falling down, it screams nice sentences to the passengers, and also it shows itself in its full beauty. That's the idea behind it. It's also running Langevad and an MSP 430. It has 10 servo motors and 1 DC motor and an ultrasonic sensor unit. And the ultrasonic sensor unit is only used to protect it because it has legs under it, and it's doing strange movements in the air with the legs, and you need to protect them when it's falling down on the floor. So it pulls them in when it's near to the floor, and it has a sound unit, of course, to say nice things to passengers. Finally, I have some background study. I very much like the photos of Edward Muybridge. It was a photographer in the 19th century, and he's the predecessor of the motion picture. He did this kind of photos by putting a large. I think these are 12. The upper side 12 photos. So there are 12 cameras where they're making these pictures, and they all place them in a large line and let animals and people run or walk by. And he becomes famous with the lower 12 photos, and that's a running horse. But he proves that horses fly a short while running at full speed. All legs came from the ground. So yeah, and looking at these photos, you can very nice see how an animal moves. Also how people move. We did a lot of photos of people, and that you can use implementing movement algorithms. Then we have some logical thinking. This was for the hexapod robot, and I did a small survey of how the legs could move with the freedom they have. So that you see here. And finally, below we see some movement patterns of insects with 6 or more legs. The upper pictures show it's called a duizendpoot in Dutch. It's the animal with a lot of legs, and that has a motion in it like a wave. It's very nice to see. I think that you all did see that sometimes in pictures. And if you are interested in it, you can find this information on the link below on the page. Now I'd like to show a few movements of robots to finish. Here we have the cord dancing robot arm, and I'm just trying to bully it, and it shows it by trying to hurt me. And now it's not interested anymore. And here we have my hexapod standing up for one of the first times when it was completely finished. It does a rattle on the legs to place them firmly on the ground. And then it tries a movement algorithm for the first time. And this one is not very successful. You see it slides. But that was the first attempt to let it walk. Here I have another one. This was the first attempt of the hexapod, the first experiments. Come, keep it big. This one was a little bit more fluid. You see it a little, it's saying hello over here. This was version 2, also saying hello. You see it has a little bit more power. And now we have a demonstration of real functioning walks. This is the crab-like walk. Walk sideways. Here it's turning to the right. Walking forward. It's a strange walking pattern, but that's because this is a commercial robot kit, and it was very badly balanced. So I had to develop very special walking patterns for it. Otherwise, it would fall over. Here it's scrolling, turning to the left. And here it's resting like a cat. This is walking on high heels. And that's it. Finally, I have some small things about Cozy. It was the demonstration for a line follower. The turning is to adjust the sensors for the current light conditions. You see it's working quite nice. And this is the second one. This Cozy, another program that it's sealed within the black line, so it can't pass them. You see, it's a little bit sad. And finally, there is some small movements of the bird-like robot. This is an experiment of the neck. Just the movement from left to right. A simple test. And finally, the wooden prototype. And just controlling if the mechanism is in principle works okay, and if the motors are strong enough to drive it. You see the wings get in and out and do a little flapping. The legs are not controlled here yet, but the head can turn around. It can pull up its feathers and do a little talking. So that's it. Any questions?
Wow, thank you very much.
Fantastic.
So I'm puzzled that I was only aware of 1 or 2 of them, and so that you had this entire collection is completely overwhelming to me. So thank you very much for showing that. Yeah. Yes. Are there any questions?
Yeah, not a question. Just I was amazed by your presentation. It's so, I don't know, all your creation. It's just not just a robot with some hardware and some software. There is all this metal work, all the design, the drawing that you do. You inspire yourself on other old photographies and just all the, I don't know, the anatomy and all the mechanical thinking that there is inside that. And also, I have the feeling they are all inspired in animals and their interaction with people, the interaction with the world, and That's amazing. Yes,
I'm very inspired by behavior.
Yeah.
So some of the robots, especially the monkey, is a bit inspired of myself. I like to work in home, so I'm comfortable here, but I need to go out to meet people and to do other things and eat. And that was the main inspiration for the monkey-like robot.
And do you expose them? Is there, I don't know, is there, yeah, okay.
Yeah.
That's great. Congratulations. Thank you for sharing.
Okay.
Willem, when did you start to build those robots?
Oh, I think in about 1985 or so, about then. But I built my first robot on the VIC-20. I don't know if any one of you do know what the VIC-20 is, but that was the predecessor of the Commodore C64. And I did earn a little money, and with it I bought in the sale my first computer with 3K of RAM and BASIC on it. So that's how it all started. And also I always like to build mechanics. My first robot were just mechanical, with a little electronics to drive the motors. And it was I remember my first article on the microprocessor, it called. Not processor, but professor. It was a small article in an electronics magazine that mentioned a single computer, a single chip computer for the first time. So with that in mind, I built the Opodal Do on a 6502.
Great. So who are in media? That's
Thomas.
Thomas. Ask your question, please. Maybe. So you have to unmute your mic. So that's might be the reason why.
I have a question. How does 3D printing making robots easier?
Albert, is it you?
Yeah, that's Albert.
Yeah, Albert.
I said Thomas, sorry. Hi, Albert.
Okay.
How does it make make it easier? Because you can make parts exactly on the right size.
Yeah, at least for prototyping, that's great.
And with the right functionality. Especially like for the legs, I should not know any other way to build it, because the wires are going through the leg, and that are not straight holes but round holes, and you can only print them on a 3D like in a 3D like process.
Right. Yeah, so in our robotics lab we use 3D printed parts all over the place. Yeah, so that's for sure necessary.
Okay.
Any other questions?
Atle is without sound, so he's writing his questions on the chat.
I'm looking to it.
Did you do the complete IK for the walking bots, or rather, do you think it's necessary?
Inverse kinematics.
Inverse kinematics, okay. Yeah.
Okay. I don't use kinematics. I just write it all out myself.
But then, Willem, how do you resolve? Do you create an array of positions?
I have an array with beginning and end position. The Philip-Plot algorithm makes them nice and fluid.
And sorry, is this a linear interpolation, what you do? Or how?
Yes, but it's a Bresenham-like algorithm.
Ah, Bresenham, okay,
Yes.
excellent, excellent.
So
This
you
is
can also make curves. You can also make and that's why I shall.
That we love to know, Atle. Atle is very interested to know that.
That's why I opened this screen. This is Albert Nijl's website, and he designed that algorithm that I use, and it's also completely described on this website. And on the Eagle pages, we have also an implementation of it for where the robot is described completely with all the parts. And here is the implementation of the Piliplop.
Yeah, very good. So I can encourage everyone to go to the Eagle page and have a look at it. And yeah, very interesting.
Especially for Atle, this is very important because we don't have many examples like this one.
Right. Okay. Other questions? Then Willem, thank you very much again.
Okay, it's nice to do.
Yeah. And
fantastic.
Yeah. And we continue with our next speaker, which is Bill Ragsdale, and he's talking about Win32 Bill.
Okay, I'm ready to share screen. Willem still has his screen up.
Okay, sorry. I'm a little bit puzzled with Zoom.
Oh, I wanted to say we have Andy Hoover in the meeting, but he did not ask anything to Willem.
So somehow I share the screen and now I stop it again and then it will.
Okay, thank you.
Yeah. This is the superpower of the model.
I lost the controls.
Yeah, I have this always. Bill, great.
We are on our way. I'm going to do an exploration of Win32 It is one of the granddaddies of the fourth systems going, has about a 25 or 30 year history, and we'll hit the high points of it. And my goal is to inspire you to investigate it yourself because its resources are astounding. So our quick summary of the installation itself. Win32 is a full featured fourth, and I mean full featured fourth, floating point, integrated development environment, object-oriented programming, and many links to your host computer. As we'll see, it is not a tiny system. It is a gigantic system. The user has 8 megabytes free, but in the dictionary, there are 5,400 words. We'll comment on that a little bit more. It also has at the bottom line, you see 20,000 Windows constants. It has in it, I understand, buried somewhere are all of the callback values to talk to Windows. The history, it was written by Andrew McEwen. I'll point out from a little bit of pride that Andrew McEwen worked for me for about 10 years back in the 1980s. And during that time, he asked if he could do some independent development work on his own. And we said, certainly. So he started his own fourth as an outgrowth. We were using Pig4. He did an outgrowth of that onto PCs, and then it grew. He left our company a few years later and continued the development on his own, which has resulted in the Win32 In about 1995, he passed it on to Tom Zimmer, who did major polishing. Bob Smith added floating point. It came back to Andrew for the final packaging and releasing. It has been updated since that time, by a European team, Anton Erdl, Jos van der Ven, and others. At about 3-year intervals, they have returned to it. I suppose when Windows makes revisions, they bring it up to stay compatible. And it's still, it supposedly can run on Windows XP all the way to Windows 10. I haven't tried it on XP lately, so I don't know, but Windows 10 is fine. So Andrew's guidelines on this were, number one, in this developing environment, the computer memory, there's plenty of memory. Our original things like Figforth ran in 8 kilobytes, and the memory space was 65 kilobytes. The current computers now, I think mine has 4 terabytes, if I remember right. So even in those days, 30 years ago, Andrew said, we'll have lots of memory, so put anything in here that you might possibly need. So that's why there are 5,000 some words. There's a lot of convenient words he has, for example, like 1, 2 to R. It puts 2 words onto the return stack. And another one is R from drop. You could normally write this as R from and drop, but it's a word and it's written in machine code. And when they got into the graphics part of it, the graphics user interface, he then added in an object-oriented system that was originally called Neon, then it was called Yerk, and then it was called MOPS. And it's internal, and all the graphics work is done in that. Andrew realized that he's going to have a huge dictionary, so the dictionary threads is variable threading. In a user dictionary, I believe it starts with 8 threads, but in the host system, it's a 157-way thread. So compilation is extremely rapidly because the search is very quick. Andrew decided to write as much in assembler as he could. So any word that is a single function, what I call little words, dupe, drop, swap, and so on, are all written in assembler. And it is remarkably a good client of Windows because it will gracefully trap memory errors. So if you access Windows outside of your legitimate memory space, it will trap the error and report it and bring it back to forth and give you a diagnostic message. And it makes full use of visual programming. There are 2 editors. There's the IDE editor, which supports the object-oriented programming very well. And then there's a basic simple editor, WinEdit. As we would expect, it's a 32-bit forth. It has all the usual stacks operators. It's ANS forth, NC forth compatible. As I said, it has an editor and a development environment. Everything you could think of, floating points, strings, files, memory allocation, it's all in there. And much, much more, including web access, audio, and images. You can type, at the keyboard, you can type web Wikipedia, and it will open your web browser and will take you to Wikipedia. So you can access from the keyboard websites. Very handy for checking a little reference. If you see something you want to check on Wikipedia, you just type web Wikipedia and you'll be there. Or you can go to any other site. So you wanted to go to GitHub, you type web GitHub and you will be there. Here's a summary, a kind of a buzzword summary of all the things that are in there. There is a beautiful single step trace. I used this for maybe 5 years before I discovered the debug single step trace, which is a lifesaver. You can use emulate, which is an ANS4 word to allocate memory. You can go into Windows and request a few megabytes of memory for a scratch pad. Full read-write access on files. It has the catch and throw error recovery, recursion, locals, linked lists. The language internally makes a very large use of linked lists. There are about 12 different linked lists, and these are kind of execution chains. so that you do a linked list of commands, and the fourth will run down that linked list, executing the commands in sequence. There's a huge number of vectored instructions. There probably are around 200 words that are actually vectored, so that when you change your operating environment, you go from editing, executing to input, output. A lot of the keywords will be rewritten or reassigned in core. It has a full floats and transcendentals. You have all the sine, cosine, hyperbolic, arc sine, arc hyperbolic, exponential. It's all there. Multitasking. You can create tasks to run in background. You have DOS commands at your fingertips. If you write DOS and then the string sequence that will execute DOS commands. And the most clever part, or careful or far out part, is the memory translation. There is a one or two words that will take the fourth memory space translate and then translate in a proper compatible way into the raw memory space within Windows. And it's a magic that I don't even want to understand. But and they are brief words. They are words of 3 or 4 lines that somehow get through the Windows veil and into the actual machine. This is a quick summary of the operators you would expect are there. The native elements, of course, are bits, bytes, the half word or 16-bit 2-byte numeric word, 32-bit cell, a double cell of 64 bits, the floats of 64 bits, and so on. All the words you would expect. There's a very, very rich format choices for numbers. You can do 32-bit integers. You can, from the keyboard, you can input 64-bit integers. You can do base selection without permanent change. In other words, you a prefix with an @ sign. You'll take a decimal number, hexadecimal prefix with a $sign. You can do hexadecimal doubles. Floating point values. If you include an E in your number anywhere, you will be in floating point input. It does not have to be a scientific notation. You can write a full decimal number, put an E at the end, and it will then become a floating point value. From applications, if you do a prefix with an F# sign or F number sign, the following information will be taken as a floating point. So it's quite easy to put floating points in. For an ASCII character, if you put in quotes or single quotes, that will be taken as an ASCII value. And of course, you can use a prefix of the word ASCII. I will make a point at this moment that even though there is this very, very rich input for formatting, for floating point output is very, very limited in floating point output. The usual integer outputs are all there, very flexible. And so what I've had to do is to do floating point output. I've got to take my floating point number, translate it to integer, and separate the integer and fraction parts, and then use fourth output formatting. So you're kind of on your own in writing floating point output. I think they probably had to reach a point of some limit how much you can put in, and there is no accepted or normal or standard output floating point for fourth, other than just putting out the decimal number. Of course, the precision is adjustable. The floating point, I believe, goes to about 16 decimal digits. So you can set the precision to 14, 15, or 16, and you will see the full precision of your output numbers. As a quick look at the integrated development environment, you see a program on the right. And it's very convenient. There's some little windows to tell you what's going on. This handles, internally it handles a form designer. There is a documentation extractor, which I don't even understand. And there's a project management component. So on the object-oriented programming, there are a number of different components that go into each application, and the project management breaks those out into the proper subdirectories. On the left-hand side, you see a quick snapshot of an application I had in process. It was doing on this word game called Wordle. This is doing some of the analysis on Wordle. So if you see running down the list, there's the letter of the alphabet. These are letter usages, and it shows where in Wordle they are allowed. So that's just a quick output for a program in process. Notice it's split screen. So your IDE is on one side and your live for system is on the other. This is a single step. This is, if you've never operated with single step before, it will be thrilled when you encounter this, because you can put down any word in your application, and when that word is encountered, it doesn't have to be the first word available. So that word could be 2 or 3 levels deep into your application. When that word is encountered, you will go into a single step, which is shown at the left. So we see a do loop coming along with the eyes and doing a word called do green, do green, do green. Then at the bottom, I've circled the I in red. And if you look at the code, the cursor on your source code follows the debug. So you will see from your source code exactly the word that you're on, that you're single stepping. So I circled the I, and you notice the I on the right in the red circle is shaded, and that tells me that is the command that will execute next. So when I hit space bar, the value, the operation for that particular I will execute. A miracle. Here's some real life examples. I just pulled off a couple of the most impressive. This is real time, it's a clock, real time programming, Win32.4. You'll notice all the dots of circles in there. So there are decorative, there's so much extra compute time available that there is a decorative pattern going on. And of course, the hands are moving in real time. So there's a clock. This is a turnkey application written in Forth, and it comes out as an exe file. So it's a standalone application with its own Forth that's portable. And here is a multimedia.
You started off with 3 cards. These 3 you don't show the spec.
There is an application written in Win32.4 that will bring up videos and play audio. There is one that will play radio. It will tune to internet radio. And again, this is done real time. Not sure we can play it again. I don't think the video is written. I'm sure the video is not written in Forth. Somewhere he's got the hooks into this to find the video that is built into Windows, I assume. So here's why I love Win32.
It's Python, Bill.
Here's why I love Win32.4. First is it has been stable for 25 years. Some course, and of course, operating systems go through revision time to time to time. Andrew pretty well got it right the first time around, and so it is a stable platform. Second thing is it has much more in it than I need and understand. I explore and I continue to find new things. For the last 10 years or so, I've kept notes on these discoveries, because I'll come back to this maybe at 6-month intervals, once a year, think of a project, come back, and then I've got to go back through the whole thinking process. What do I know, where it is, how do I find it, and so on. So those sets of notes grew to be about 100 pages. And thinking about it, I've come up with what I call the cosmologic model of Forth. Cosmology is the study of everything. Cosmology is the study of the known universe. And so the cosmology of Forth is the study of Win32.4. And I won't go into the specifics here, but each of these, it's a new way of factoring Forth, so that in preparing the documentation, each square is a documentation module. So you can see where I'm leading to. I'm taking my 100 pages of notes and converting it into a book with major expansion. And so I'm building on, of course, the original 132.4. What we found out is most of the books on fourth were written in the 1980s and 1990s, and they are out of print. I'm not aware of any books written in fourth that are unique and original in the last, say, 5 years. So most of these books are out of print. What I hope to do is put this book into print in such a way that it will be available, forever. Most of the books are quite historic, and most are not ANS fourth compatible. Of course, this fourth is, and my book will be. The key on this is that Amazon makes publishing and distribution painless. If you submit a PDF in the proper format to Amazon, they will publish it, they will sell it, and it will be available as a print on demand, and you get a royalty. I have another book that's right now is printed on Amazon. So if you all would like to get my current book in print, Google for John Scarney Ragsdale, and it will take you to the Amazon link. So John Scarney is a magician from the 1920s, 30s, and 40s. He's been kind of a hero of mine. I've done presentations at conferences on him, and I'm the world's authority on this magician. So Google John Scarney Ragsdale, take a look for my book. And I realized how straightforward that is. Now I'm writing my second book, which is going to be on Win32.4. It is in textbook format with full exercises and full index. Most of these books do not have decent indexes. My Scarney book has about 40 pages of references, and it has a full index of every word in the book. And I intend in this Win32.4, because when I go to buy a new book for technical use, the first thing I look at is the index. And if there is no index, I will not buy the book, because I cannot flip page to page to page to try to find things. So to me, the most important in any single book on evaluation is there an index. The working title on this book is A Cosmology of Win32.4, the complete fourth textbook. There's a prototype cover. And now, gentlemen, pay close attention to this, because this is another revolution going on. 2 days ago, I became aware of the interactive chatbot software and graphics. So I went to Stable Diffusion, registered, and I typed in, my first entry was a galaxy on a star field for a book cover. It was a galaxy on a star field for a book cover, and this is what Stable Diffusion generated. No cost. The time was a few seconds. That's astounding, amazing. There are several other ones. There's DALL-E 2, there's Midjourney, there's Stability AI, and these are graphic, and there are several that are text. The alternative to this would be going onto something like WeWork and spending from $100 to $500 to have a cover art done. And here it is, free and immediate. So here's why you need this book. This fourth has many levels of help built in. It has the ANSI fourth, it has theory, it has practice, it has glossary, full glossary of all words. But to use it, you have to know what you're looking for. And so, for example, the words associated with cell, there are 6 of them. There's cells, cell plus, cell minus, plus cells, and minus cells. To find them, you have to know their name. If you don't know what you're looking for, you won't know where to find it. So the idea is my book is precisely structured for recovery. So when you want to look for math, all math in the entire book is in one chapter. So if I want to do stacked math, I have one place to look, and that is in the math chapter. It is not spread out between integer, floating point, and so on. So it is organized for quick reference. The current version is PDF. It's available on GitHub. If you go to my name on GitHub, Bill Ragsdale, it's the Win32.4 manual. It's the about 100 pages, and it is in very clean but note format. In other words, you will see notes to myself, comments to say move this to another section, and so on. So it's a working document. So that covers my activity. It is Win32.4. I commend it to all you folks in the Windows world and give it a try. It is also downloadable from GitHub. I should have put a reference down there, but if you go to Win32.4 on GitHub, you will have it available. And that is it. I can take questions briefly if we have any, and we'll stop sharing.
Thank you very much.
Wow, excellent.
Yeah. So that's a great decision to bring your experience together. I know, Bill, you're right there from the beginning. And yeah,
I still have the floor. Let me make one ego-driven comment. We saw a fantastic presentation on 6502 written in Forth. I will point out the original Figforth model that I created was done in the 6502. So we have come in a full circle. Figforth started on 6502. By the way, it correctly handles the indirect jump. 6C, I believe, or 6F. But look back at the old Figforth model and you will see Forth code, or you see Forth assembly code for 65.2 scattered throughout. So thank you very much. It's been a pleasure. Thank you for the loose use of the hall.
Yeah. So are there any questions to Bill?
Yes, Christian has a question.
Christian, hello. Sure.
Bill, I'd like to hear your opinion on the number of words in general with Forth. As a beginner, I was always amazed at the number of words in the dictionary. In normal life, I use maybe 500 words in French. And when I work with Forth, now I end up with, in your case, 5,000 words. How can a human being use that many words?
Well, that is offered for the impact that it has as a number. There are about 7 vocabularies in Win32.4, and one of them is called hidden. And so stuck in hidden are all the little glue words that make things work. So I don't remember the number offhand, but I think there's about 2,000 words that are in the hidden vocabulary. You can certainly access them, and they are in the source code. The system comes as 8 megabits to begin with, and it installs, and it has all the source code for everything there. And from the keyboard, you can take any word, and if you type view, it will take you to the source code. So if you wanted to see the source code for the word quit, you just type view quit, it will take you to the source code. If you want to see it in memory, if you type C, S-E-E, C quit, it will disassemble it from memory. So these are your links to exploring Forth, is by looking at an object code in memory and the source code. In the Forth vocabulary by memory, I think there are 1,500 words, 1,000 words, something like that. In a minimum Forth system, I think it's about 200. So we have gone from 200 words to a minimum Forth system to maybe 2,000.
Yes, it's basically 200 words. It's not, you don't need, Christian, to know 5,000 words. The problem is the interface to Windows. When you want to interface to Windows in any language, not only in Forth, you need so much APIs calls to the functions.
So what you're saying, Peter, is that most fork in general, we use only about 200 words. We have a selection
150,
of fancier words if we want, in the 4,000 that are in kind of libraries. What you call word list or whatever.
In vocabularies, yes, like Bill, yes.
Yeah. I think the 200-word number I pick off the top of my head, but I think that is to have a running forth system that says okay, and that will talk to mass storage. A couple hundred words and that's it.
Does fork have more words to remember than other languages, like, I don't know, Java or C or?
I'm not, can't comment on other languages, but I think if you look at most high-level languages, there are in the range of a couple hundred keywords, probably in some cases not even that many, maybe around 60 or 70, that are the core that make it operate. This would be an interesting study for others to compare between languages. What would you consider the functional minimum to be able to accomplish, work? How many keywords are there?
I know one thing, as a beginner, it was always a challenge for me to remember what was in there in fork.
Well, that's why we have put things in a very modular basis. So one chapter is interpreting only. Doesn't talk about compiling, it's just interpreting. It's what can you do from the command line. Yeah. Another chapter is locators. Well, the locators are all things like that locate memory, which is constants, variables, arrays, create. So if you want to create something, you just go to the create chapter and that's all. There's no math in it. There's no stacks in it. It just takes how do you create a word.
Bill, a lot of the words are I thought, window constants. There are a lot of window constants to call
20,000, Willem.
Yeah. That makes a large dictionary.
What is it that has 20,000 functions?
20,000 window constant functions.
Boy.
I think they should be in a separate vocabulary.
Well, they definitely they're invisible. They're way in the background. And
okay.
They basically are, I think, are hexadecimal values. It's a hexadecimal value that you pass to Windows that controls callback communications. And so Forth is given these 20,000 values names, I guess, or string equivalents. And in a proper format, you pass that hex value to Windows and you accomplish whatever the task is.
Okay.
Andrew saves us the effort for mastering all of that. all I care about is to set a path and a directory and open a file, and that's about it.
One of the ways to answer to Christian, these graphical environments, Christian, were never meant to be programmed by hand. They were meant to be programmed by other programs. We have in Windows 32 Force the form designer. And this form designer creates, and he knows these constants and names, and we don't use these names. It's made by another program. This program creates these interfaces.
Okay, I think I better understand all this. But yeah. I realize that programming in general is quite a memory challenge.
Yeah, so it maybe it's a good topic of some future workshop or so, how to do UI programs with Win32 Force. So I think that's really something on the other side. So where we see apart from the embedded system side, things that you do for application programming on PC? That would be great.
Excellent. Ulrich, are we going now to the next speaker?
I think so.
Well, I will present Ulrich Hoffmann with a new, his new presentation is /////.
Yeah. Here we go. So I think, let's see. I hope you can see it. Yeah. Do you see the first slide?
Excellent.
Yes. Okay, great. So then let's see how this goes on. So I would like to talk about the many personalities of quote. Yeah, and so let's have a look at what this could be. I give a short overview of what I will be talking about, and I try to be short and keep in the 15 minutes talk time. Yeah, so first there's the string personality of quote, and we will have a look at how quote is actually no longer used, but C quote and S quotes are. And then we will see a little bit of how you could implement it. And yeah, second is the gaming personality of quote. And we will have a little bit fun looking at the game. And well, this is not really serious, but it shows that you can define everything in force if you want to. There's the tidy personality of quote, and I will not talk about that today to keep the presentation short. Then in some sense, there's a friend of Xlab, and if you count the number of dashes in the title, turns out to be 38, and so we will learn what 38 has to do with this, and then we come to some conclusions. So it's a not complete serious talk, but maybe you'll get some nice ideas from it, and we will see. So traditional in force, if you look at the fig force model, for example, or those force systems that run in very constrained environments, we represent strings by so-called counted strings. So, which means we have the length encoded in a byte, and it precedes all the characters in there. There's the fourth word count that extracts this count byte and puts it along with the beginning address of the characters on the stack. And then you can work with this. And traditional also parsing for source code returned counted strings. And yeah, then some people came to the idea, well, maybe the drawback of this is you cannot have strings that are longer than 255 characters. And if you want to process measurement data, for example, then and put them in strings, or you have long text lines, then you can't really go with that. So there's another representation that is very typically used, and that's the so-called C-U or C-len string representation. A string is represented by two items on the stack, and that is the beginning where the characters are located in memory, and the number of characters on top of the stack. And the drawback of these two notions is actually, or the situation that we face is that different force systems use quote for either one or two. So either it denotes counted strings, or it denotes C-len strings. And so if you want to write portable programs, you cannot use quote to get a well-defined behavior, because you don't know what the system will actually do. Does it put one item on a stack or two items on a stack? Do you need to use count on the thing that you get, or whatever? And that's the reason why in the standards we have S quote and C quote to make things explicit. And so in a program you can explicitly specify what you really want. So I have some examples. Volksforce in the first line, which is a Forth 83 system. It has this quote, and it actually returns a counted string. So if you define the word test and you run it, then you have to say test count type to actually get the string xlab put out. And in GForth, which is a standard Forth 94 and Forth 2012 system, you see quote or S quote for that, and then you either have to say test count type, like in Forth 83 as interpretation in FoxForth, or you don't use count to actually get the string output. And so let me see. This is really strange. I don't have a mouse pointer whatsoever, and the Zoom dialog is somewhere on top of these things. So I have to remember what is on the right side of the slides, but that is not so much an issue. So now that the quote word is available, because you can't rely on its behavior anyways, we can define it in application programs, whatever we want. So let's have a look at how we can do it. We can define a quote compiler, something that will run or we compile code that eventually, when run, will put a string in our desired representation on the stack. And for this, I choose the C-Other-Len representation. So we have this definition of quote, and it will actually parse the input stream, and it will then, by parsing, get C, other, and U as a representation of the string, and then it compiles this information as a string literal into the dictionary. And since we want to use this inside colon definitions, it has to be immediate, and it's only supposed to be used in compilation mode because it just compiles code. It's not interactive at all. Yeah. So given this definition, you can run it and use it in a sample definition where we define test, and now we use our new quote character. And since we've programmed, we know exactly what it does. It uses this C other U notation. So, and then we can say test type and get the appropriate result. So maybe we also want to use things in interpret mode. So a string interpreter would not compile any code, but would just parse the input stream, extract the string from the input stream. But then this raises the question, where on earth should we put the string so that it can be used? Well, we can put it at here, but then parsing will immediately destroy it, probably. Or we could put it at pad, which is somewhere distant from pad, but as soon as we compile something, that's also not available anymore. So where else to put it? And well, my idea is, well, we could just abstract this away, say, well, we have some kind of word reserve that will actually give us some amount of memory, or some memory that we can use. So again, we parse in the interpretive version of quote, we parse the input stream, get character address and a number, but then we want to put it into some safe area. We use the number of bytes to reserve an appropriate memory, get some additional memory that is safer than the memory returned by parse, and then we can put our string there. And if the nice thing is that if we do this again, then we get, with reserve, we get another piece of memory, and so that our strings are longer living than just a single invocation, which is nice. And so we can use a line like the one below, which is xlab wanda type space type, and we see both strings are still active, and we can use it. and we can allocate memory as much as we want to do it. Well, sort of. Yeah. So let's have a look at how this reserved word looks like. And the idea here is, well, it has this stack effect. You ask for allocation of a certain amount of bytes, and what you get is an address where allocated memory is and the length. And then you can use this memory with the appropriate length to put in whatever you want. The idea here is that it allocates bytes from a buffer, which I call the shelf, from top to bottom. And if no more space is available, then we try to reuse old memory, overwriting what we earlier had. So it's only for scratch, and you have to know what you're doing for scratch information. And but the reserved areas have somewhat longer lifetime than just putting the data on pad. On the right, you see a drawing of how this works. So there's shelf, with which is the buffer, and there's size, which is the number of bytes in this shelf. And there's tick free, which is a pointer to the free memory that we get. And we start at the end of shelf, and with every allocation that we do, we decrease it in an appropriate way. And it might be that we don't have enough memory below free to satisfy the request. Then we restart over and reset it to the beginning, and so on. So it's in essence, it's a circular buffer, but the implementation is very easy and very, very simple. So so that works quite nicely, and you can do it. So that's the string personality. And the next one is the gaming personality. Since quote is available, we can define it whatever we like. And so it could also be a game word. So quote with several dashes could start a new round in our word guessing game. And the number of dashes that we use could determine the length of the word to guess. And for playing the game, we use the force interpreter. So we use quote and some dashes to actually start the game and then try to play it. Yeah. So we say something like, well, let's start with five letter word, and we try the letter O, and it's there on second place, and we try X, it's not in there, we try O, we try R, we see it, and then we recognize what it is. We can try the entire word and see that we did it. So, and let's see how we can work with this. Yeah, let's give it a try. Maybe I do something like 1, 2, 3, 4, 5, 7, 8, 9, 10, something like this. 9 letters. Well, let's try try 0. Okay, yeah. Well, that's interesting. Try F. Oh, this looks. Try T and H. Haha, I know what it is. Try 4th. Try 2. Here we go, Force 2020. Okay, so quote is also a nice game, and so that's another personality that we have. So, and well, this comes to my conclusion. Well, I'm a great fan of the Xlurp word, which is the word that cannot be found in a dictionary, and it's used in starting force as the specimen for the word that you don't find in the dictionary. The difficulty is, if you want to explain it to someone, you have to make a dictionary entry, and that counterfeits its purpose. But yeah, and its relatives or its friends are the words that are the longest words in any language. And since my title is a word with 38 characters, the question is really, what is this word with 38 characters? I looked it up. In Dutch, there is a word for that, actually. So like German, like German, the Dutch can also chain words in a great way. And I don't know if any of you can guess what it is. It's the longest Dutch word, which is...
I know one long word. Another one I know.
So this has 38 characters. Meerwürdige Persönlichkeitsstoornissen, or something like this. You can teach me how it's pronounced correctly. And it means multiple personality disorder.
Yeah, meervoudige persoonlijkheidsstoornissen.
Yeah. So that concludes my talk. So we looked at the string personality of quote, learned about counted strings and C-Adaline implementation, looked at a very simple primitive circular allocation. We saw compile and interpret implementations of quote. And we had a look at the game, which is very easy to program once you have this things. And yeah, we looked at the long Dutch word. Thank you very much for listening. Are there any questions?
Thank you, Ulrich.
All right.
Nice.
Yeah.
I have a question.
Yeah.
Why don't you use allocate for reserve? I've done that a long time ago, and I have no regrets.
Yeah, you of course you can use allocate in a system that provides it. It's optional actually, and in the standard, so it might be too difficult to implement on in small embedded systems. So that's mainly the reason. And I just sat down and said, well, normally we allocate from the beginning, or yeah, if you use allocate and have your own implementation, it uses this block mating and try to defragment the memory, but it seems to be more difficult than this. So this reverse allocating of the memory, that comes to me as a very simple approach to do things.
I posed the question wrongly because I didn't mean allocate, but a lot.
I see.
There's a lot in the dictionary.
In the dictionary, if you want to, yeah, could be. The only drawback that I see is that it might conflict with whatever you do on the top of the dictionary. Maybe you're compiling a table or whatever, and you don't want it to be disturbed by strings that you use. Yeah, but it could be that it's easy to circumvent that, and then a lot would be fine, which is upwards allocation. It's in classical bump, so-called bump allocation. Yeah, could work.
And then the other, since 2002, I have meant to kill the guy with the mustache. He's doing something for Ford that is absolutely necessary. He divides the input stream according to blanks. And I have, if I am looking up quote, it is found in the dictionary. Even if the word following is the character following is not blank, and that is called the prefix, and and you can look up normal words via this same mechanism, because it matches perfectly if it is followed by a blank.
Yeah.
And then the idea is that quote something quote is considered in effect a double number. So
yeah, and it's a new way to describe string literals, and so I think that's just another personality of quote. So to be able to be attached to the string directly and then denote the appropriate CRLN value.
Yeah.
Great, yeah. So yeah, we need to talk about the prefix algorithms once in a while and tell more people about it. I really like it.
Yeah, but of course, one thing you shouldn't do is postpone such strings because it is a number and you can't postpone number. If you you have to postpone numbers, you must use literals or something like that. And of course, Anton Oertel hates this situation that you are obliged more or less to inspect state. Yeah. Okay.
Right. Yeah. Thank you.
That was the remark.
Yeah, Klaus.
Yeah, I would also like to raise the question of state smartness here. I can see no reason why it would be forbidden to bind the compile and the execution action into one word by just using state fetch if and
so
else.
that's I know this is a very difficult discussion, and it's not easily explained where things go wrong. But Anton has written lots of paper about why this is difficult. And I think the easiest way to do it is, yes, combine it, do state fetch, but then make sure you never postpone a word like that. So then you don't run into this situation, and keep the factors so that if you want to do and use it, you use either the interpretation or the compilation word later on, then you can use it in an appropriate way. So the issue is that the state smartness will stay, and if you compile or postpone a word like that later on, then the decision whether you're in compilation mode or interpretation mode is not at the right time anymore.
Yes, Uli, is it not possible to forbid such actions?
Yeah, but it's difficult to test, but yeah. So, yeah, you should not postpone it. Postpone has to look for it and then raise an error. Yeah, that would be possible.
Okay.
Right.
It's easy to do if you postpone a string in my Ford. It says that is not a word, and it is not a word, it is a string.
Right. Well, thank you very much for listening to my talk. And yeah, I think now is the time for ESP32 fourth workshop, or do you intend to have a break?
Yes, we are going to have a break because it's very long, this meeting. And we continue in 15 minutes, if you all agree. And the next one will be Jason. So in 15 minutes, I am going to bring a coffee and start again, or everyone can stay and chat.
Okay, folks, I will be going, and see you again next month. And next month, I have planned to give a presentation on poor man's case.
Excellent, excellent, Klaus. We are very happy.
So bye-bye.
Bye, Klaus.
Bye.
Nice weekend.
And I
come back in
away.
15 minutes.
It's time for dinner for me, so see you next time.
Yeah,
see you.
I have to drop out as well, so you see my picture, because if the host leaves, then that's will be a disaster.
Bye,
but I will be away. Bye-bye.
I'm not sure. I'm using 7.0.6.19, but I think that version doesn't have the assembler and disassembler, right? In fact, I'm not really sure where to get the new one with the assembler. Any comment on that, Brad? The latest bleeding edge of ESP32
There's an assembler disassembler. It's a little bit of a work in progress. There's one issue is that the operand order is mixed up with a few of the opcodes, and I also haven't added a high-level flow control yet.
Oh, actually, we didn't. At least I didn't hear most of that.
Oh. Yeah, your sound is like going.
Let me try again. It has different microphone. There we go. Is that better?
Yeah, much better.
Yes.
Yeah. So yeah, in the bleeding edge version of ESP32 there's an assembler disassembler for Extensa and for RISC-V5. It's got some rough edges. It is not sort of fully vetted in terms of the validity of the opcodes. I'm sort of working on figuring out a good testing procedure. The other issue is that some of the opcode orderings are kind of scrambled. They tend to be based more on the ordering in the instruction rather than sort of any coherent order, although they tend to be source destination predominantly. I had to put a poll up on the 4th 2020 Facebook and got people to vote about like which ordering, and I'm going to try to homogenize it. And then I've got a couple ideas about how to automate some testing to compare it to objdump, so I get a consistent result. But it's usable enough that I've been able to use it to poke around. But you sort of need to not make any deep assumptions about the ordering of the operands. And that's only in the bleeding edge one right now.
Never let them know your next move.
So, one more time? Didn't quite get that.
Never let them know your next move.
Yeah, no kidding.
Keep them guessing.
Hi, Brad. This is Christian.
Hi.
I just heard you talking about the assembler, disassembler. I just want you to know that I was very glad to hear it was appearing in the ESP32 I always wanted to be able to create some short words in assembler without having to go back to C. And I think now I'll be able to do it. Was that a bit of your intention behind this as well? Probably as
yeah, a little. I sort of two intentions with it. One was to the possibility of those kinds of things. Although depending on the type of binding you end up like, I find I'm rebuilding it constantly, and so it's sort of like if adding a thing isn't a huge deal. But the other thing that actually got me down that direction is the disassembler, because I was interested to poke around with some of the internals of the system and experiment with it, and that's actually one of the things that led to the talk that I'll give today is with fault handling, is that I was trying to figure out, can I do fault handling on the ESP32, and I actually did use my disassembler to help me sort of find my way a little bit in terms of being able to add fault handling. So.
Will this also help to better understand the expressive API, the big binary blob?
You can go poking around in it, and in some sense, I ended up using a mixture of both looking at what was in memory and then also looking at the source code. And I think in some sense, I sort of found my way to the right place in the source code by of the portions that are open source. But you can go through the veil into the heart. There's parts of it that they've open sourced, and then there's some parts that are they just distribute a binary blob, and those especially. They have sort of a hardware abstraction layer that once you punch through it, you don't get to see what's inside. And so you can, to some extent, do that, just on a desktop with objdump. But I find that being able to interactively poke something sort of helps you figure it out. Like with a fault handler, one of the early experiments that I did was, well, what happens if I change out this value and see what happens, and does it change the behavior of the system, that type of thing.
See, the problem I always have with the expressive API is I never know what it expects as data.
Yeah.
And that might help to figure it out. I might be able also to create things that are harder to create in Fort as data structures.
Indeed.
But that's way beyond my expertise right now. But I'm still curious about how all this works in the APIs. And it has everything you could ever dream of. A lot more than what we already do with the ESP32 Fort.
But even so, I think with the ESP SDK and the IDF, a lot of things more or less just work, right? I've been doing a lot of STM32 stuff recently, and we had to use the SDIO peripheral, and you know, there's a lot of very thin documentation, and you know, Doxygen generated documentation that just says, you know, timeout is the value that specifies the timeout, and you could actually, well, yeah, I know that, but you know, how, you know, what is the way to specify it? Because there are functions that ask for clocks, and then there's functions that ask for milliseconds, and so on and so forth. You know, so yeah, irritating doesn't quite cover it.
It's frustrating for a lot of these. I mean, even with the ESP32 stuff, like there's so many layers and they've stacked upon what's in the libraries that they provide, and it's sort of amazing to trace through. And it's like, wow, you had sort of one abstraction and you wrapped it in another, and you wrapped it in another, and so yeah, and that seems to be pervasive. A lot of this, it seems like it's like just tell me where whatever control register is in memory, what you know, what bits it expects.
Yeah, absolutely.
You were mentioning Doxygen. It's a kind of program, if I remember well, that extracts documentation from a source code. And why do we have to rely on this? Why isn't the programmer providing proper documentation to start with?
Because people don't like to write that stuff. It's boring.
Because I think a human being at writing text that is understandable will always be better than whatever shortcut was written into the code itself.
Yeah, of course, Doxygen is not capable of writing the documentation. It has been written elsewhere, and my experience is that all documentation generated by Doxygen is worthless.
As a beginner, what's frustrating me reading other people code is the fact that most of the time I have to spend a day understanding the code because there's not enough details in there for me to understand. People make it very, in Fort particularly, they make it very short so that it compiles us fast on a limited CPU or MCU, and then it becomes almost impossible to understand by a beginner. So they extract all the comments and they just leave the code there.
Yeah, I agree, Christian. That's one of the frustrations for me as well. And one other thing that would be very, very helpful is if people would put a comment at the beginning of which standard are they writing with, you know, because I'll be trying it through one program, you know, G4 or whatever, and I'll run into words that don't exist or are different, and it's just very frustrating to have to try to figure out what was this code written on.
I just wonder if it's worse in Fort than it is in C or Java. Do people document better in other languages?
Okay, guys, we are back to the meeting. Okay. We keep chatting a little bit more after the workshop, Christian, no problem. And the next participant is C-J Tay, and he will show us C5 stack with ESP32 forts. It's a preliminary presentation. You need to unmute, Jason.
Yeah, okay, here I am. I've just got a little bit to share, so I'll just I believe I'm going to share. Okay, well, let me share this. Okay, I've got to share multiple windows. Okay, right. So for those who don't know, the M5 stack is actually basically an ESP32 that has been dressed up in a molded plastic housing. It has some helper. I believe it does have it breaks out all the I/O pins into a little header inside it. It adds a gyroscope and accelerometer. It adds buttons. There are versions with touch screens. There are and it features 2 Grove connectors as well. And it starts out at about $40, which sounds sort of expensive, but you know, if you need to rapidly put a very sort of nicely built version of the ESP32 ready to go with the screen and speaker and all of those basic things, and attach it to your project, you know, it comes ready built with screw holes and magnets and so on to attach it. So now directly ESP32 Forth will run on this, and so it has become the subject of interest for my implementation of something at work, which is this actually. So I need to control this device here in the middle in white. If you actually look at it, what you see in front of you are actually a whole bunch of distillers. Technically speaking, so the one on the left is actually a water distiller that my father bought like 30 years ago. They still make them like this. It looks very pretty in glass, but a bit fragile. And then I've got this electric water distiller. And then I've also got a reflux distiller on the right. The sharp-witted amongst you might realize the irony of this, but what it is that we've actually got a license to distill alcohol in a Muslim country, thanks to the old British colonial masters, and that's what we're using today. And so ultimately, the goal is to distill gin in this device here. And the way it goes is if you let it do its thing. Actually, it's trying to distill purify water. But you know, there's lots of people who have gotten it to you know, to do the evil bidding, and it mainly comes down to controlling the temperature, right, of the heater. So that's what I've been working on, and the intention is to let me see if you can see my speaker window, my camera window as well. You can see the device here. It's I've got a special version that has keypads on the front, and so far, if you just load ESP32 Forth on this, it'll just run like an ESP, of course, and you won't have use of the screen and so on. So what I've been doing is that I've been adding support for the M5 specific word sets just in the user words, and all of these words are up on the GitHub for the group, and it makes it pretty simple. And I think so that's what my February presentation is all going to be about. And yes, well, obviously, you know, if it works well, then I will have some nice gin to drink. But you guys will be watching apparently. But you know, hopefully it might inspire or enable someone to try the same.
Well, the next time you present how to break the law with ESP32 Forth.
Yeah. You watch out for the licensing requirements in your country.
I am really waiting for this because we talk very much with Jason about all his amazing installations, Brad, of your work. And it's incredible. He and Christian and Jan Langevad and so many others in the group, myself, of course, we are enjoying so much.
One of the interesting side effects of using switching to fourth on the M5 stack is that well, you know, of course, I suppose the usual users of M5 stack will say, oh yeah, but you can get this interactive behavior on Python as well. But you know, I still feel that nothing is as immediate and gives you as much freedom as forth, in fact. And as we all know, ESP32 forth is 3 times faster than MicroPython. And MicroPython still requires quite a lot of structure. You know, you still need to type quite a lot of structure in order to use all these words. You know, one of the things that Peter was advising me on was to try to find, you know, words that are as short as possible. And under MicroPython, you know, you'd have to type the whole shebang, right? You'd have to type the whole damn thing, which is not necessary. And then on the other flip side, if you were trying to do this in Arduino and C, you know, you change one line. You know, you're trying to build a user interface. You change one button, the placement of a button, the color of a button, the shape of a button, and then you hit recompile. You know, it's a long wait, right? But you know, and that's where, you know, ESP32 forth really comes into its own. I can type these commands and get a change to the user interface instantly, and that's radical, you know. I don't know if I don't know if I should stop sharing at this point, but for example, I've got it set up to do a little demo. It's got a temperature sensor in it, which is one of the things that I'd be interested in. So, you know, this is getting the ambient temperature right now, and if I hang on to it, it's going to get my body temperature, and you can see it's gone up to 36 degrees, right? And if I let go of it, it'll drop down again. You know, easy peasy, right? And you know, I can do things like hey, you know, guess what? I need a red bar at the top, right? Oops, something happened to the screen.
I removed your screen. Do you need it?
Oh, no, I don't need it.
Share again, no problem.
No, it's okay. Okay, give me a minute. Yeah.
This way we can see your full screen.
Yeah. So, you know, if I decided I needed a red bar on it, one line, and that's it, you've got your red bar instantly.
Fantastic.
You know, it's really instant feedback. You just can't do this almost any other way.
I have a question, Jason, if you allow me. So you were controlling the M5 stack or the ESP32 forth via serial terminal?
Yes, yes, I was. Yeah. This particular one has an attachment for keypads. I'm not running it directly on there, simply because ultimately that's not how it will be used on to control the distiller.
Yeah, because the keypad is more for the user interface while you program and you have the. Okay, that's great. Nice little piece of hardware.
I'm just impressed by your distillation efforts. That's it's impressive.
We should try to show this to other M5 stack users.
Yes, that's right.
To find a group of them and show them.
Yes, that's right. Just to experience the power of it. Yeah, and you know, I can show you the let's see now. Yeah, so this is actually the source code for that demo. Yeah, you have almost, I mean, the most involved thing there is actually the you know, the math for the converting the beta value, you know, and the ADC value into Celsius, right? But everything else is you know, pretty easy going, right? It's like there's hardly anything there. And I'm sure even this can be simplified as well. I just took the textbook formula and started from inside the logarithm and worked my way out. And that's it. So hopefully, yeah, I mean, when February rolls around, we'll have the whole thing working nicely. And who knows, you know, maybe in a few years' time, we'll be controlling the main facilities with ESP32 Forth as well. Brad, are you planning to get some ISO certifications for ESP32 Forth?
Hadn't been on my list, certainly.
Amazing, amazing. Excellent, Jason. Any questions?
How accurate is the temperature sensor if you compared it to a...
Well, I mean, it depends on how good or how crap a sensor you buy, right? And then, you know, you have to do your 2-point calibration and so on. And then you have to factor in the, you know, which ESP you've got, because the older ESPs have a non-linearity, and then newer ESPs supposedly Espressif introduced a fudge factor in the firmware, and it apparently takes up this, you know, that brings you to one of the things about the ESP32, right? The amount of available static RAM can be different, because sometimes they've got some binary blob in there to fix the ROM.
Yeah, that variability with the memory layout is a bit of a pain. It seems to be a little bit more consistent on the Dash 2, at least, from what I've noticed, but still, it's, yeah.
Yeah, one would hope so. Well, even apparently the RP2040 has come a cropper with some ADC problems as well, hasn't it?
Okay. Then if we move to the next speaker, if there are no more questions for Jason, we move on to Jan Langevad. Are you there, Jan?
So, can you hear me now?
Excellent.
Okay, good.
Jan will talk about the touch sensors or the touch interface for the ESP32.
Okay, can I take the screen?
Go ahead.
So, here we go. You see it?
Perfect.
Okay. It will be a little hard to have a demonstration after a man who can control a boost machine, but anyway, I'll try. Maybe I can keep you awake, I hope. Let's see. I looked at this map of the ESP32, and as you already have noticed many times before, maybe there's some touch input, and someday I would like to play around with those. but I found out that there was no direct support for the touch in the manual, so to speak. So I contacted Peter, and with the help from Peter and from Christian Hinze, I got up on the track and could finally use the touch inputs on the ESP32. On my version of the ESP, I have 9 touch inputs, and in my first application I only use 5. So let's see what we have. Just a second here. Here we go. And maybe you can see my camera. Yes. Can you see a box here with my hand?
Yeah.
In the right side? Oh, great. Okay, that's my first idea of an application. I have a box, and it's very fine. I can almost compete with the Boost machine now. You can see it's designed by Porsche. It's very, very fancy. No, in fact, it's just a box from a lazy USB disk that was kaput, and I took out the box, or I took it out of the box, and now I have a plastic box here. And I started with 5 locations for using touch, and I must admit, in the beginning, I wanted to use galvanic separation. In other words, I would not like to touch an input going directly to a pin on the processor. But it was very hard to interface because the signals were very floppy, so to speak. So in this version, I've given up on that principle, and those 5 dots here are directly connected to the processor. I wanted to use some chips. I had some chips, a little semiconductor that could take a pulse of many thousand volts. But when I put that on, the touch pads didn't work, because it worked almost also like a capacitor. So I could not protect the input pins using that one. So in this version, it is connected directly to the touch input. But this one is an old ashtray here, and it's of metal. And when I touch this, I should get rid of all of the high voltage here, I hope, because it is connected to the ground on the ESP, and through the USB cable, it is connected to the ground in the house also, I hope. So there should be no big difference in potential from my hand here and to my fingers. It should all be grounded. So up to now, the hardware is still alive. No accidents with the sparks here. Just to say, show you there's some life in it. The sound is not very high, but maybe you can hear it. It could be used for a lot of applications, and today I will only talk about my problems in doing the implementation of hardware, software, and not on applications in detail. Maybe another day I could present some, but obviously you could use it to Morse, and I'm a radio amateur myself, and maybe someone could hear what this is. This is. Well, if there's a radio amateur there, they could recall that was a CQ call to anybody. And that application has been optimized a lot of times. You see, I have here a Morse key used for radio amateurs and professional too. And believe it or not, Morse is still in active use. Thousands of people are using Morse right now. And of course, Morse has been optimized, and you know it's hard to make the right lengths of dots and dashes. And a lot of guys have made computers that can help sending Morse code correctly, so it will shape the writing of the user. And that is one application I could use it for. Also, I think maybe if you had some persons with some handicaps, maybe only one arm or whatever problems they had, maybe touch interface could be used. But I would not recommend using touch input if you just need a simple contact. It must be a special application. Ideally, all those points should be down below in the plastic box. You can see that's how I started. You see, I started out with some silver, and you can see a lot of examples on YouTube where they start using the touch interface here, and they all show a wire and using some paper, metal paper here, and of course that is working. I could see the signals changing when I touched on the front, when I only had that one. But as I told you, the signals were very hard to see. It's much better when you can do the touch directly, and I hope it will survive. Okay, you see there's a buzzer in here and an LED, of course, but otherwise it's very, very simple. I have a boot switch here, and a mode. I can boot, and I can put it in a special mode if I want it to do something special. But all the applications are not done now, only some demo and test. I can show you some of the problems we are getting when we are using the touch. Let's see. The software you see now is a short demo of the Morse. Sorry, here it is. Very, very simple loop here. And that is the finger 8 here, and the little finger is giving the value of 1. Next one, 2, 4, 8, and 16. So in fact, you have the 5-bit Bordeaux code here having 32 different possibilities. Of course, it's very hard to send a 0, but you can send from 1 to 31. The 0 is hard to obtain. So now I can show you some of the problems we get if we do a little test with one finger. Just a second. Uh-oh, it's very simple here, but I cannot find my code. That is strange. Maybe it's cut out, sorry. Here we go. Yes, here's a simple test that's only reading the signal on one touch, and I can do it on this, the 8 finger here, and I have the finger 8 test. I can just copy this one and send it. Just a second. So I have a little problem with the zoom. So here we go. You see, now I'm reading a value of 72, and if I is getting my finger closer to it, might, yes, you can see the number I get from the touch input is falling to 70. If I put my fingers on all the other ones, you can see maybe it's going even lower down into the 60s. But when I touch, it goes down to 0. That's because I'm nervous maybe, and my fingers are a little wet now. Now it works very, very fine. It's going all the way to 0. When I was reading the touch through the panel, through the plastic box here, the numbers was going from maybe 60 to 40, or going up and down depending on what was happening in the house. But when I am using directly touch here, the signal is very, very, very clear. You see, So stop that one. And where the application really is coming in is if I'm reading all the 5 fingers in at the same time. That is giving me 31 possible inputs. I will test that one, test 5 dots. So you see here, got 16, 8, 4, 2, 1, and of course I can combine them. The value is first being read when I lift one finger, so I can do it very slowly. That's the 1 value, the 2, and the 4, and when I lift one finger, I will get the 7, or the 8 and 1 is 9, and so on. So that is in fact the 5-bit Bordeaux code using I'm producing here. What I'm using those different numbers to is depending on the application, of course, and that will follow another day. I was having the luxury of 1 week's holiday last week, so I didn't complete all what I had wanted to show you. But that is showing you some of the problems and why I is going back to having direct contact from the CPU to my fingers. That's not the best way of doing it, but there are lots of information on the internet on how to find and do that in a better way. I think Peter has sent me some links to how to do those touchpads in a professional way. Just a little comment on implementation. I was surprised not to find touch input words in the dictionary, but it has to be added. And Peter told me how to get it, and it's here somewhere. Yes, and Peter, both Peter and Christian gave me some hint. It has to be added into the user words. It's only a few lines that has to be added here. Okay, I think that should do it. No more applications for now. And I wonder if anyone has any questions.
Excellent, thank you.
Thank you.
Anybody has any questions for Jan? Then we move on to Brad Nelson, who will show us the new, let me see, the new fault handling for ESP32 force. Go ahead, Brad.
Can you hear me?
Yes.
All right. So let me tell you about a new feature that I've added in the bleeding edge version of ESP32 force. Oops, if I can. So what do I mean by fault handling? So a fault is something where you're doing an illegal read or an illegal write to some piece of memory or executing that memory. It also can include dividing by 0 or potentially even a user interrupt. And what do I mean by an illegal address? Well, memory that's not mapped, memory with the wrong permissions, unaligned memory, things that you're sort of touching and something is not sort of right about them. And if you've used ESP32 forth, probably even a little bit, you've probably seen one of these guru meditation errors. When something goes wrong, it will panic and it will crash, and you'll get a register dump. And this they're being actually a little bit humorous in reference to guru meditation. It's actually in reference to an old Amiga error message that was in turn an inside joke inside of Amiga. But regardless, these are kind of annoying because you lose all of your state and you have to restart, and so big hassle. So my goal with this was to turn these kinds of faults into regular forth exceptions, because that way you can respond to them in your program if something goes wrong. If you're interactively debugging, you'll maybe get pulled out to the forth interpreter, but you won't lose all of your state. And so just to be even more concrete, the idea would be if you did something like read from the 0 address, which normally would crash the system, if you have some word that if this was buried down deep inside of your program, you could catch the error and then get some kind of a code back out the other end. So and these are the kinds of faults that I mainly had in mind: memory reads, memory writes, calls. That's actually not the right call instruction for ESP32, but and then divide by 0 is another one of these. And actually, it's if you do it at kind of the lowest levels of the system, it's possible to do this for failures that happen down in the C code, so down at the lowest levels of the system. So why this approach? Like, there are some alternatives. One possibility is that you could, at least for all of the pieces that are in forth, you could modify the core words that access memory and make them do additional checking, check if they're out of range, check if you're touching something that's going to go wrong. But that's tricky because, for one thing, it's going to cost you performance. It's also actually not entirely trivial to figure out on a CPU like ESP32 with all kinds of things mapped in the memory, which ones are appropriate to touch. Another possibility, this is what Dr. Ting had done with earlier versions of ESP32 forth, is to contain forth inside of its own sort of virtual address space. And so you would have a portion of the memory, and he used this also to be able to have essentially a 16-bit forth, at least in terms of the memory, for ESP within the ESP32. This is nice because then no matter what you touch, you're just sort of smashing the memory. But current ESP32 forth gives you kind of unadorned access to raw memory, and so this approach would be hard to take. So what are the parts that we need to implement to do this? Well, we have to be able to intercept the fault first and get some control back when something bad happens, and then we have to be able to resume back to a safe state in forth. And so in theory, this is sort of straightforward, but there are a lot of practical problems, right? On most systems, this happens through some kind of a thing that's like an interrupt handler or similar to an interrupt handler, or literally an interrupt handler. And then there are special instructions that typically have to happen if you're going to resume back from one of these interrupt handlers. And it's a little bit hard in high-level languages to respond to these kinds of things because the stack may be in a bad state, and also global structures can be in a bad state. It can be unwise to kind of keep going deeper in the stack. So a bunch of problems, and even C finds this hard. You have to be very careful when you're writing an interrupt handler. So lots of wrinkles. And especially in higher level languages, you have this kind of contradiction where you're trying to handle something very low level, that something has gone wrong with a memory access, but handle it at a high level. And so you need to. It's actually very a lot of different ideas have been tried on different operating systems to approach how you might deal with this in a way that resolves the fact that on the one hand you want to be able to potentially resume or fail or go somewhere else, but you also want to use normal code, but normal things are in a bad state. Maybe you're in the middle of a locked section of your memory allocation routine or something. And so there's a sort of an unfortunate history of people kind of layering more layers upon in different operating systems and different approaches to this. And it interacts poorly with threads and a whole bunch of other problems potentially. So when I first looked at tackling this problem, and I'll kind of skim a little through the Linux and Windows stuff because I think folks are more interested in ESP32. But I started with Linux partially because I wanted to make sure I could do it right somewhere where I kind of knew how the thing worked. Because as you'll see in a sec, it actually took a little bit of a deep investigation to figure out how to even do this on ESP32. So on Linux, there's this API called Signals, and there's a different option on Windows. We'll briefly touch on that. So, but then ESP32 was a fun adventure. So, so Linux, there's this system called Signal that lets you register a signal handler for a variety of different signals that a process can receive, and there's a different response depending on, there's different signals for different events that can happen to the program. This was replaced later by a system called SIG action. So Signal is very simple. You just give it a function to call in response to a particular signal. This worked okay back when there were not threads in Unixes and just processes, but more complexity as they added threads, you have more need for some flags and some options. One other kind of special wrinkle is that if you're dealing with an exception that's happened sort of while you're on the stack of your program in C, you can end up in a situation where maybe you want to just leave everything alone and then go and have a different stack somewhere else. And so there's affordances to be able to arrange for the signal to be handled somewhere else. And there's also wrinkles about if you've got a process with multiple threads inside of it, which process will handle the signals. And then, so that's kind of the interception part of the problem. On the restoring to fourth, well, you need to restore the fourth registers, and then you have to get back to a coherent point because you might be sort of partway through an opcode. So you need to get kind of back into next. So the thing that I want to piggyback on with ESP32 fourth is exception handling, and this is the exception handling code. It's actually done in marginally high level code where you store away your floating point stack pointer, your data stack pointer, all under the return stack, and then you sort of stuff away the previous handler and then chain to the next handler. And so whenever you're throwing, you're kind of walking down this linked list of different handlers that are sitting on the return stack that have different points that you can restore to back on the data stack and the floating point stack. And fortunately, handler is sort of externally visible. And so all you have to really do to restore fourth is to do a restoration similar to what you would do in a regular throw. And then you have to make sure that you get back into that next routine. So the restoring part isn't too bad. I added one additional system variable so that there's a consistent place to go and figure out where the current throw handler is. And then you can pull out of that and then just use the unpark process, which is very similar to what happens whenever you yield back to C and then come back into the ESP inner interpreter, if you've ever gone spelunking in the plumbing. So this is sort of all it takes to kind of do a throw from the C side, which is something that doesn't, up until now, hasn't happened sort of anywhere else in the system. But then you have the problem of, okay, that's what you do to restore things for the fourth interpreter state. What about the fact that your program might be off down in the middle of some C function call? So you need to be able to do a global go-to to anywhere. And in C, the conventional way to do this is with a pair of operations called set jump and long jump. And the idea is that set jump stores a snapshot of all of the registers of the system at a certain point, and then long jump allows you to go back to that point in the system, passing a value that comes back into set jump. And so initially, when you call set jump, it'll just return 0. but then later you could call long jump with a 1 from somewhere else, and you'll arrive back where you left. The stacks will get unrolled, and sort of the C state will get restored back to that depth in the system. So the way I jam this into the inner core of ESP32 is this is sort of inside the 4th run routine, and then this part isn't really relevant, but there's down in the second half of this function, this is sort of first half, and then the second half, there's an initialization section that happens once. I have 2 sort of places I have to add something in. I have to add in some setup code during the initialization, and then this place where I've got fault entry, well, that's the moment where you're about to enter next for the first time. And then from there on out, you're sort of spinning around, jumping between opcodes and executing next. And so if I can do those 2 things for a given architecture, and I use this both for Linux, but I also use it for ESP32 sorry, the ESP version of a version of this. So both with Windows ends up being a little different. So to do these 2 things, the entry point to the fault and then the setup, I keep a couple of thread local variables, and these are things because you may be doing this on multiple different threads within ESP32. And so I keep for each thread a jump buffer, which is again one of these non-local go-tos, a snapshot of the register state, and then a place in a global, or rather a thread local, to store whatever signal happened. And then at the point where I want to enter back into ESP32, I snapshot the register state calling setJump, and then later if I return to this point from a long jump, then I go ahead and call that throw method that updates the ESP32 state. And so then I can just provide a signal handler. I need to be sure in the signal handler to clear whatever the current signal is. And then I also go ahead and store away a record of what that signal is, so I can use that as the number that I throw from 4th. And then I long jump back to resume back at that set jump. And then to set things up, I just have to install that signal handler for each of the different signals that I want to handle. And so SIGSEV is a memory violation. SIGBUS is like an alignment violation. Although on x86 it doesn't actually fire. And then Control C is SIGINT. And there's weirdly actually a floating point exception in Unix parlance. Early Unix actually threw exceptions for things like floating point errors, but modern floating point returns nans, but they reuse the same exception for integer divide by 0. Floating point divide by 0 gives you a nan. So Windows, very different story. I'm going to breeze through this because it's maybe of less interest to this group, but Windows has its own mechanism that's actually a little bit like the way that a 4th throw catch frames work, where you build up a chain of things on the stack, and then there's a way to just do a try and a catch and a finally that can leverage that information. On x86-64, it's actually they're able to stash this in what's called unwind information. So it actually ends up not using it stores it's stored in a way that uses less information on the stack, which is clever but very complex. And in any event, what you're able to then do is do things like have a piece of code, and you can have something that looks like exceptions in C, but it's actually able to intercept any fault that happens in the system. So one's even very low level faults. And then in the expression there, you're actually resolving this critical problem for low-level exception handling, which is you're making the decision whether or not you want to continue ignoring the exception, you want to search for a different handler and sort of throw up the stack, or you want to execute some handler. Well, so what I end up doing, and again, here we're in the Windows version of this inner loop, similar unparking stuff. because the Windows version uses switch for dispatch, because I was the Visual C compiler does not support computed gotos, I ended up needing to use this kind of an exception handling plumbing. So I wrapped the entire inner interpreter loop in a try, and then I have an exception where I do that one to check for the to assert that I do want to have my exception handler run, and then I just throw the exception which does a goto. So I don't even have to mess around with signals. In one sense, it's simpler. However, control break was an odyssey, and I spent a ton of time on this. I'm not going to go into too many details because this is Windows stuff, but basically it turns out that for receiving a control break on Windows, there's a separate API call to register a handler. If you reset the console in any way, it loses your handlers, which took me a good while to figure out. And then most critically, it handles that control break on a different thread than the one that has faulted. And so how do you move things back to the main thread? Well, the idea that I hit upon is that from the thread that is running the control break handler, I can crash the fourth thread. And so I add an instruction to do the setup. I store away the state of where the main thread is, and then during setup I record the stack pointer and the base pointer. For each of the different architectures, had to handle it a little differently, and then at the moment when a control break comes in, I pause the fourth thread remotely, suspend it, alter its registers, move around the stack pointer and the base pointer, and then resume it and let it crash, and essentially get a jump to the 0 address, and that gets interpreted as an intercept, and then you're able to hit control break. So ESP32, how to do this in ESP32? Well, folks have all seen the panic handler. It triggers for most errors. It doesn't seem to have a lot of documentation. There are a couple of various GitHub threads describing how you might do things with it, but it was a little bit tedious to trace through the documentation. There's a couple of bugs to the ESP folks where somebody had there's one bug where someone had a feature request where, oh, I'd like to be able to do something in response to the fault handler, but it turns out they weren't trying to do a programming language with a resume. They were simply trying to be able to capture a crash dump. And so they wanted to resume to a crash dump. And unfortunately, in that particular bug, they were satisfied once they added some additional facility to capture a core dump to storage. And so that didn't accomplish the goal I would have cared about. But as I dug into the Extensa documentation, not in the hardware manual, which usually has all of the like ESP32 specific stuff, but rather in the instruction set manual, I noticed that there is an exception option, and it turns out that it's on for ESP32. And what it does is it references the idea that if you have this, remember that the Extensa instruction set includes support for lots of optional features that can be turned on and off. If you support this, then there's a jump. It will jump to a certain location in memory that's not specified. Apparently, it's selected by whoever embeds the Extensa. So the ESP32 folks had to pick this location, and so I went spelunking. I had one hint from knowing that back when I first learned about this instruction, this CPU, I knew that there were handlers for it uses windowed registers, and so if you as it slides the register window in and out of whatever range, there's a handler that is used if you have to spill the stack. And so I thought, well, maybe this is where these things are at. And it turns out that, in fact, there's this table of jump vectors in memory. And down here at the bottom is this user exception vector. And these are all uniformly spaced, except there's up at 50, there's they used a little bit of extra space to stuff in part of the code that's shared between several of these handlers just to, I guess, be tighter for space is actually literally what they say in the comment in the code. And this is actually an adventure of me finding things through poking at the CPU that I could have figured out potentially by looking at the source code, but it would have been challenging. So I tracked down that exception vector in the Extensa source code, and it calls another routine after it's sort of gotten out of the entry point to an interrupt to another routine, this user exec that examines a special register that lists the cause, and it decodes that cause, and then it dispatches to a load store handler that, for a while, I thought this was the place I had to plug in, but it turns out the load store handler is merely figuring out where in memory, what kind of a load store fault it is, and then it actually comes back. And then it calls a handler from this table in memory. And so there's actually a table in memory, I discover, that is in fact the place where it handles different faults depending on their number. And so early on, I was just confirming, I put zeros in there to confirm that if I clobbered the handler for a given type of fault, that instead of getting the guru meditation error, I would just get a complete fallover of the chip. And so then I discovered, looking in the source code, they actually have a C-level entry point to let you set one of these handlers. It's not mentioned in any of their documentation on the website, but in the source code, there is this symbol, and this symbol is available even in the Arduino build, and you can install a handler. So I can then create a similar version to what I did on Linux, where I still use set jump and all of the same logic to restore, but instead of a signal handler, I have one of these handlers that looks at the execute frame. I'm even able to pull the cause out and stuff that into the same signal variable. And then I have to restore things. This is actually took a while to figure out. If you don't call this XDOS restore interrupt level, what ends up happening is you can recover just fine from the exception, except that the watchdog timer does not understand that you have recovered. And so a few seconds later, the whole system comes crashing back down. And so you have to sort of do this, or else eventually the watchdog will trigger it. And then you can register for a whole bunch of different errors. So load store errors, privilege errors, access, divide by 0, illegal instructions, and a set of other load and store errors. I'll demo in just a second. What about RISC v5? Well, because as folks know, there's the ESP32, the S2, and the S3, which are all Extensa based. RISC v5, or the C3, and I believe the C6 now that's coming, are RISC v5 based. I haven't gotten as far there. I've been doing some similar spelunking. I've discovered that there is a table of jumps that leads into the panic handler in this global called vector table. And unfortunately, this memory, unlike the ESP32, where you can kind of write to code memory, the RISC v5 will actually panic when I write to this table. So I'm not able to just directly alter one of these tables. There isn't, as far as I can see in the code, a way to a call similar to the set handler option to register your own handler. But it looks like what I may be able to do is call this other ESP CPU interrupt set address, which is actually documented in their public documentation, to specify an alternate interrupt table. So I may be able to replace this entire interrupt table with a different one that's able to call into my handlers. This panic handler that it calls into is pretty much a direct thunk straight into the one that prints Guru Meditation and all of that. So I'll have to swap out a few of these. And this may be a little hard to read, but this is actually a repeated series of identical. Some of these go to the interrupt handler, some go to the panic handler. And so then coming things is RISC v5. The other thing is I haven't done a good job yet documenting what numbers it throws for different errors, because it varies depending on Linux or Windows or ESP32, and might even vary by versions. With that, let me very briefly pop up a different window to share. So I'll first just show things in Linux, just to show a couple of things there. So the most basic thing is just that if you read from 0, you get an error now, and that's nice. And what's going on underneath is if I take the address of at and do catch, I'm actually getting signal -11 here, and it's the same story if I do a write to 0 or any other invalid location, I'm able to intercept that fault. If I do internals and then I do call 0, or actually I guess I can catch that as well. So those are all great. Another nice thing that I can do is if I define some test word, for example, and I read, or rather, sorry, let's suppose that I did a print, hello, and then I wait 200 milliseconds, and then I go again. Normally, if I ran such a word, now I'm stuck, right? If I hit but because Control-C is now converted into an error, I can Control-break out of it. I'm still in fourth. I still have the interpreter there and can resume. So those are all great. The same thing works under Windows. Just as I mentioned, it was a heck of a trick to get it to do the Control-C. And then let me go ahead and pop up for an ESP32, just for so here's on an ESP32, and in some sense it's much the same story. If I read from 0 or I read from some arbitrary location, I'm going to get an error. If I Control-C does not work currently in ESP32. This is actually one I need to put a little thought into, because right now the terminal handling sort of intercepts it, so it doesn't really make sense. But it would be kind of handy to be able to Control-C to terminate things. I need to put some thought into whether I really want a message coming over serial to block things in that particular way. For ESP32 fourth, if folks have opinions, I'd be curious to hear about that. Oh, I forgot to show divide by 0 throws as well, and again, these are all different signals. On ESP32 fourth, I believe it's different. You get a different signal for different types of operations that in Linux are treated as equivalent. So you're getting like a -28 for the read versus the write. Yeah, so that's the feature. Hopefully it will make life simpler for folks as you're debugging. It'll be harder to crash things. It doesn't have any overhead to the system particularly, because it's just being done at the hardware level, and that is it.
Excellent, Brad. We need to try this out.
Could I ask you quickly to put a link in the chat so we can get this code? It looks lovely.
Yeah, I'll link to it. So it's the bleeding edge version on the ESP32 fourth site, but I'll post those in the chat.
Great, thanks.
I have a question about what catch does. What does it catch any exception?
Yeah, so before, catch would only catch exceptions that were explicitly thrown by either your own fourth code that called throw or parts of the system, like some of the IO words. Now with this fault handler installed, errors like memory accesses and jumps to invalid instructions and things like that will all throw and turn into an exception you can catch with catch. So catch will catch everything. Yeah.
All right. That is very, very nice. In Forth 2012, the exception word set is mandatory. I think they also specified what the exception numbers should be. So if you,
I should probably homogenize mine to match some of those numbers. I think if I'm, yeah, I think that sounds familiar. I feel like I've seen a table of numbers, and so I probably should try to do a conversion step and bring these in line. I think as you saw, like the saga was just getting the mechanism, because I wasn't even originally certain that I would be able to do this on ESP32 Forth. There wasn't clear documentation anywhere that ESP32 could do this, and it turns out it can, which I'm relieved. One thing I have noticed, by the way, already on RISC-V5 that will be almost certainly different is that they seem to treat it they don't treat divide by zero as a fault. In fact, they do something peculiar. I believe they return -1 if you do a divide by zero in RISC-V5. So I don't know what the story is on that one, but so unfortunately that one probably, unless I'm willing to make the divide operation less efficient, I probably will not be able to make that throw, but probably will stay with what the native architecture does there.
Probably at the lowest level, you should have an overflow flag set. And the libraries should check for this.
I suppose one other thing that I could do well, so on Linux, the stacks for Forth are currently in contiguous memory. So if you have a stack overflow, I do periodic checking whenever you kind of go back to the interpreter to see if you've fallen out of range on the Forth stacks. But I probably should now, in Linux at least, I can isolate them and surround them by guard pages. So if you overflow that way. Maybe there's a place in memory I can do something similar on ESP32, but the challenge is that unfortunately the usable memory in ESP32 is all kind of, it's not all contiguous, but it's in a bunch of chunks, and there may not be a good place to put ideally you would put a stack in a place where if you overflow out into an illegal address and then it immediately catches it. But so I might do some investigation of that, but that's a different type of tweaking.
I'm sorry. Does the RISC-V have a memory management unit?
I believe it does, or at least it seems to have a little bit more of something. At a minimum, one notable difference that I've found is that where in ESP32 you can just write, or sorry, Extensa, you can just write to code memory and just clobber the code if it's the right sort of memory. With RISC-V5, it at least understands the notion of page protections of a piece of code is not modifiable unless it's been sort of mapped in that way. So
amazing.
I think there is something there. It seems to be more elaborate than what Extensa has.
I will present the next participant, Brad, who is myself. And my presentation is about ESP32S3. The new chip. Let me show you what I found. So the S3 is the new model. Manufacturers are sending this device in different embedded products now, because it has a lot of advantages, and this is the replacement for all the chips we know. So the next chip you will buy will probably be this model, the S3. And it's not the same as the C3. The C3 is the RISC-V, and this one is still the Tensilica. So I have also in my device the TN graphics display. So I will do 2 demonstrations And this is what the S3 is able to do. It's a dual core like the others. It has 500K of RAM, but it has a new Bluetooth, the number 5 LA. This is very important for modern connectivity. It has 45 programmable pins, GPIOs, and a high-speed flash. In my case, I got also the PS RAM. I will show you in the next slide. Another important feature is the AI acceleration. This is important for cameras and for speech interface. This allows a neural network to run much faster, and it has a total support for these applications, ESP-HU and ESP Skynet. Then you can get all this information from the eExpressive site and go after this guy here. You can download the user guide and the PDFs, etc., and read all the interesting news. There is also an improvement in the security of these devices. All things customers were asking since many years ago. And what happens on the interface in Arduino? This is the most used interface for us. And you see all these switches for the compiler. We didn't have this on the other models. And so you can, this is what I was, I had almost 1 week fighting. I was fighting 1 week with these switches, and I am still a bit confused because it's a lot of different possibilities. And if you make something wrong here, your code will not compile. So I will make later for the group a short picture of my setup so everyone can follow it. It's very simple. In my case, my device has 16 megabytes of flash. And I am using partition that Brad recommends, and it works well. This works well. And then my device has this OP PS RAM, and this will be different for each device you buy. It will be different. You must take care. You can run on Core 1 again, events where your events run. So you have a lot of possibilities which are very interesting. Of course, you need first to put your module. You see here is S3. You need to the first step is to set up your board. Well, this is about the S3. So in the past meetings, you've seen I implemented the TFT display with touch interface for ESP32. This is the old one, the room, the normal one. And I had to add all these cables, even if this is a SPI interface, it needs almost 8 cables because you have 2 SPIs, one for the touch and the other for the display driver, the 9488 in my case. But the chip is 7200 something. I can't remember the number exactly. Then you have all these cables, as I said, which in the new in the new displays that I am going to show you, it's not necessary anymore. This is the one I bought. I bought this model, which is an integrated display with the ESP32 on the back. Here you see the antenna. And this device is the S3, is the new S3. It comes with 16 megabytes of flash, 8 megabytes of PS RAM. This is a serial RAM, and it's used internally. I am not using this RAM from ESP32 force. And of course, it has a capacitive touch interface and TN display, which is very bright and very nice. Resolution depends on the model you buy. In my case, I bought this one, 480 by 270, but there are different displays, so this is up to you, what you choose. And here you see from the back, you see the ESP S3, this one, and you see 2 buttons for boot and reset, a SD card like the other display had, also the same one, SD slot. And here you have, for expansion, a SPI interface, which is, I think it's this one, with this kind of connectors, this GS 1.25 millimeters. It's a SPI interface, and it comes with the cables. So you can use these cables to a breadboard. You can use sensors and different expansions. And then you have also a power supply here for a LiPo battery, and your USB-C type. This is a C-type USB. And here you have another one, another UART, the second COM, with the same connector, GS 1.25. And the cables are in the package. So it's everything there. And here you have also another extension, which I am not using in the moment, but this for a camera. So you can add here a small camera on the top, and it will work together with the display. And what else? Well, here you see ESP32 force running well with the device, Hello World. The device is very, very bright, so it's difficult to adjust my camera, but I will show you later a live presentation. And here you see some of the words I implemented. The basic, this is from Adafruit library, GFX. So everyone who worked with the display before will know. I only added at the front of the names the TFT name. So you have TFT ellipse, TFT triangle, TFT rotation, TFT pixel, line, text color, text size, cursor ink, circles, etc., etc. You have a lot of words on the user words, of course, and it works very, very well. It's very nice and steady. I let one of these chips running for 2 days without problem. Very nice. And I wanted to show Brad here. You see the Force Dictionary. You have over 200K free. You have almost 210K free dictionary. This is amazing. Amazing for such a small board, for such a small CPU, that we have such powerful force and dictionary. And it's almost illimit